see if it's ringing. I'm considering trying to build a Chrome extension that allows for text-to-speech because it's annoying me how slow this one is. Like if it's for short text, it doesn't matter that much, but sometimes I wanna accelerate more and it doesn't allow me. But I think that building a Chrome extension might be too hard or take too long. Like one exactly like this. But the only difference would be that it allows me to go faster. But yeah. So I think now I'm gonna study. I read a bunch of different articles already about proof of stake. I'm gonna continue reading these articles here in the documentation from Ethereum. And I'm going to continue to study the source code. This is gonna take a lot of time. Yeah, now I know roughly what each file is. I think I'm going what each folder is. I think I'm going to study the files themselves and try to see what each one of them does. Maybe use ChatGPT as well if I can, if it's still available, to clarify a little bit more on how does it work. The whole mempool and uncom blocks thing, that is confusing.
The body here, let's have a div, and let's have an H2 tag, which will contain our title, which will pretty much be the same thing. Let's call it actually upcoming Toronto concerts. And now we need to have an unordered list, which is really just going to contain the foundations, and then you can kind of an async function called fetch data. And this is where we will be fetching the data from our API we will use. Which, speaking of API, let's go to it. So I signed up for Rapid API, which I'm late to the game of, but I'm obsessed with. There are so many fun APIs to play around with. And for this, I used the concert. Here we go. Concert. So I was going to use Eventbrite for this. When I was looking at the docs for Eventbrite, from my understanding, and I quickly scrolled through them, so I might have missed it, but from my understanding, with Eventbrite, it has to be, you can only get back your events that you created. It doesn't really make sense. So I found this API, Artist Events Tracker, and I really liked it. It was just very simple. You can get upcoming events, events of artists, past events, and I really wanted events by location, so that's what I did. And if you haven't used Rapid API before, it's super friendly. All you need to do is select which kind of endpoint you want, and for this one, I said events by location. Then if I go down, you can see the name, which is the name of where you want the events. So for me, I'm going to put in Toronto. You can also select the min date and max date. So for this, I'm just going to do for the next upcoming days. Otherwise, it's a really long list. So let's go today until let's go Wednesday. Why aren't you? Number pages 1, and then test it out. I also want to use JavaScript fetch for this, but like there's so many, it's really cool. Like I said, I'm kind of late to the game, so let me know some really cool APIs if you've played around on Rapid API that you really like. And if you haven't, well, here is your a little bit of information to go check out Rapid API. This isn't sponsored by them or anything, but I'm really excited. I found it. Okay, test endpoint. Okay, 25 items, and then you can see here. So what we will simply do is copy code, which includes our fetch of the API. We're passing in the options up here, and let's just add here, paste that in. Then if we go here, let's kind of update this a little bit, so you can see
I think
here.
shortly at some point I should complete this article here as well. And I think I'm gonna, because a lot of these questions here are already answered. So the point of Flashbots is that they allow you to have a private auction, which like the node has an option to propagate the transactions to other nodes, or it has the option to, after receiving the transactions to its mempool, you can auction the transactions to block builders, and then block builders build the blocks, and then they send that to the node again. I think it's something like that, but it's still very confusing to understand like exactly how it works. Because on Flashbot's documentation, they say that the searchers send bundles to block builders, then the block builders, each block builder, there's several of them. Each one specializes on one thing, and then you have to see which one you trust. And then from those block builders, they send the transactions to a relayer. And a relayer is just an RPC provider that connects to a node. And the relayers send the transaction to the MV boost, and the MV boost picks the best blocks from the relayer, and then it sends to the validator. And that's the whole flow of the things. But it's still confusing, like, because if you take all of that away, for, let's say, and you, like, let's say you don't know any builders, for example, then you would send the transaction directly to a validator. So the thing that I don't understand really well is like, it seems to be centralizing by nature, because you have to know, you need the connections for the builders, or because you depend on flashbots. So like the whole part of the centralization happens before the mempool part. And then once you get to the mempool, then it already went through the whole funnel of optimizing the transactions in the block to capture the most MVV. So that means that it's through centralizing, because like there's nothing you can do if you don't have the connections to the builders, and if you only have access to a public RPC, let's say, then you're fucked either way, because like you are at a massive disadvantage, because when you send the transaction to the mempool and it propagates through the other nodes, then you are gonna be front run and all of the other stuff. So it becomes this politics game where the RPC providers that capture the most of transactions and have the best connections with the best builders capture the whole market, and they control everything. In which this case is flashbots. So I don't see how, like, it doesn't seem to me that is the correct solution, but I think that they are working to find ways to decentralize more. And I'm also studying this, thinking about this stuff as well, because like I'm still not sure if I'm going to build. I don't know what exactly I'm going to build, and if I'm going to build on Ethereum or not. Ethereum to me feels like is like the duct tape solution. It doesn't seem like it is the best out of the other ones, but I don't know the other ones as well, the other protocols. And if I am going to build something on Ethereum, then it's obviously important to understand how the MEV works, because it's going to impact the applications. Because the whole infrastructure of the thing depends on the types of transactions that are made and the whole order flow, and how the users are going to interact with your application through these RPC providers. So I think that anyone can build, and anyone can build an RPC, let's say, because the only thing that an RPC allows you to do is to send connections to a node. And what a relayer does is pretty much just connecting to user, is like passing your transaction to the node. So it's essentially like creating another layer of API between you and the node. That's what the RPC allows you to do. So for example, let's say you create a server, then people can send transactions to the server, and then you can put some logic in the server, and you build your own node, for example. Then you use the RPC methods to connect to your own node, and then as the transactions are sent to your application through the user interface, then you select which nodes are gonna you're gonna send the transaction to. So in that way, you can control which nodes which mempools are gonna receive those transactions, because you control the flow of information to each node. And then each node has the option to decide whether or not they're gonna want to propagate your transaction forward in the network, or if from the mempool they're gonna pass that transaction to block builders. They're gonna try to optimize the flow of the order of transactions to have the best MV possible. But this thing, I'm not really sure. I'm not sure if they optimize. I think they optimize before. So before it goes into the mempool, like, and that's the point where it depends, because like if you send the transactions directly, then there is no way to protect, because it's gonna go directly to the mempool and then it's propagated. But if you send through specialized builders first, and then the builders send to the mempool, then the block is finalized by the time it gets to the mempool. So, like, even though in both cases the transactions are propagated through the network anyway, through the mempool. In one of the cases, what's propagated is the full block that is already validated, and in the other case, you're sending the transaction should be put inside of another block, and that's the difference. So it seems to me that the main difference is just the size of the block and just the size of the block. Because in one case you send the full block, in the other case you send just the transaction. And then what happens is that this I'm not really sure on proof of stake, but on proof of work, what used to happen is that different nodes would have different histories of temporarily different histories of blocks because they validate blocks at different rates and they create their own chain. And then what would happen is that they have communications protocols that allow them to understand which ones the history that their neighbors have. So they're always comparing the history that the local history that they have with the history from their neighbors, and whichever one becomes the biggest, it becomes the official one over time. So although all of them have different histories temporarily, eventually all of them converge to the same one because there's one history that grows more than the other ones, which is probably going to be the history that is common to most of the nodes, but it's still very confusing how that happens. And I don't understand really well how the mechanism of disregarding the local history in order, let's say you're a minority node that has the wrong history, like how do you disregard your local history to accept the one that is the longest? Like that's the stuff that is confusing, and proof of stake is more confusing. So that's what I'm trying to understand now.
Here, right now we're doing fetch and passing in options. I'm just going to delete this for now to start from scratch though. And let's give this a name. Let's call it res response. And let's await. So we get the response to this API. Then we're going to have something called record, which will turn the response into JSON. Perfect. Now let's just log out that record here. Perfect. As expected, nothing comes up on screen because constants. So here we go. And we will pass in item.name. For this example, for the purpose that it will show you really how you can put anything here you want, whatever kind of content you want. Let's do version. So the version of it, let's do, this is going to be the first on 1.00. And let's make it upcoming Toronto concerts window. And in Chrome here, navigate to more tools, extensions. From here, all you need to do is turn on developer mode, load untapped, and you can see how testing's out. But let's go to, where is it? Here we go. And just select the folder where your extension is. And look how cool that is. It's so easy to do. Upcoming Toronto concerts. Amazing. So now if we go back, refresh. Here we go. And we can see our upcoming Toronto concerts. How cool is that? As you can see, there's a lot more we can build onto this, from dates, from actually linking out so we can go get tickets for the concert. But I didn't want to make this video go on for too long. And I really wanted to show you just the implementation of getting the Chrome extension and building out how simple it is. So leave in the comments if you continue building this out and what you watch look like, or what other functionality we should include.
I guess it works just like a page where you just code the page as if it was a page, but then the CSS is going to be slightly different because of the way that it is structured. That's the thing that I don't understand. So how I think it's not just normal CSS, JavaScript, and HTML to create this, but how different it is than creating a page. And then you put the scripts here, the event listeners to change the rates, which I was seeing here. I'm not sure if it's worth it to do this though. Like if I get really annoyed and then I have more time after studying all of this stuff, and once it gets to the point, because I think that building something like this would help the blog as well. That's why I'm considering making this. I should probably try to make it first as a component to incorporate on the blog, and then see if I can make an extension. But I'm not sure if it's worth right now. So I think I'm gonna wait. If I get really annoyed with the speed of this, if I get more annoyed, then I might put in work to build the extension.
The reason why this only works for short-range forks is simple. The user has to have the right to withdraw the security deposit eventually. And once the deposit is withdrawn, there is no longer any incentive not to vote on a long-range fork starting far back in time using those coins. One class of strategies that attempt to deal with this is making the deposit permanent, but these approaches have a problem of their own. Unless the value of a coin constantly grows so as to continually admit new signers, the consensus set ends up ossifying into a sort of permanent nobility. Given that one of the main ideological grievances that has led to cryptocurrency's popularity is precisely the fact that centralization tends to ossify into nobilities that retain permanent power. Copying such a property will likely be unacceptable to most users, at least for blockchains that are meant to be permanent. A nobility model may well be precisely the correct approach for special-purpose ephemeral blockchains that are meant to die quickly, e.g. One might imagine such a blockchain existing for a round of a blockchain-based game. One class of approaches at solving the problem is to combine the slasher mechanism described above for short-range forks with a backup, transactions as proof of stake, for long-range forks. Top OS essentially works by counting transaction fees as part of a block's score, and requiring every transaction to include some bytes of a recent block hash to make transactions not trivially transferable, the theory being that a successful attack fork must spend a large quantity of fees catching up. However, this hybrid approach has a fundamental flaw, if we assume that the probability of an attack succeeding is near zero. Then every signer has an incentive to offer a service of resigning all of their transactions onto a new blockchain in exchange for a small fee, hence, a zero probability of attacks succeeding is not game theoretically stable. Does every user setting up their own Node.js web app to accept bribes sound unrealistic? Well, if so, there's a much easier way of doing it: sell old, no longer used, private keys on the black market. Even without black markets, a proof-of-stake system would forever be under the threat of the individuals that originally participated in the pre-sale and had a share of Genesis block issuance eventually finding each other and coming together to launch a fork. Because of all the arguments above, we can safely conclude that this threat of an attacker building up a fork from arbitrarily long range is unfortunately fundamental. And in all non-degenerate implementations, the issue is fatal to a proof-of-stake algorithm's success in the proof-of-work security model. However, we can get around this fundamental barrier with a slight, but nevertheless fundamental, change in the security model. Weak subjectivity. Although there are many ways to categorize consensus algorithms, the division that we will focus on for the rest of this discussion is the following. First, we will provide the two most common paradigms today. Objective, a new node coming onto the network with no knowledge except I, the protocol definition, and 2, the set of all blocks and other important messages that have been published can independently come to the exact same conclusion as the rest of the network on the current state. Subjective, the system has stable states where different nodes come to different conclusions, and a large amount of social information, i.e. reputation, is required in order to participate. Systems that use social networks as their consensus set, e.g. Ripple, are all necessarily subjective. A new node that knows nothing but the protocol and the data can be convinced by an attacker that their 100,000 nodes are trustworthy, and without reputation there is no way to deal with that attack. Proof of work, on the other hand, is objective. The current state is always the state that contains the highest expected amount of proof of work. Now, for proof of stake, we will add a third paradigm. Weakly subjective, a new node coming onto the network with no knowledge except I, the protocol definition. 2, the set of all blocks and other important messages that have been published, and 3, a state from less than n blocks ago that is known to be valid can independently come to the exact same conclusion as the rest of the network on the current state, unless there is an attacker that permanently has more than X% control over the consensus set. Under this model, we can clearly see how proof of stake works perfectly fine. We simply forbid nodes from reverting more than n blocks, and set n to be the security deposit length. That is to say, if state S has been valid and has become an ancestor of at least n valid states, then from that point on no state S which is not a descendant of S can be valid. Long-range attacks are no longer a problem, for the trivial reason that we have simply said that long-range forks are invalid as part of the protocol definition. This rule clearly is weakly subjective, with the added bonus that X equals 100%, i.e. no attack can cause permanent disruption unless it lasts more than n blocks. Another weakly subjective scoring method is exponential subjective scoring, defined as follows. Every state S maintains a score and a gravity. Score, Genesis, equals 0, gravity, Genesis, equals 1. Score, block, equals score, block.parent, plus weight, block, asterisk gravity, block.parent, where weight, block, is usually 1, though more advanced weight functions can also be used, e.g. in Bitcoin, weight, block, equals block.difficulty can work well. If a node sees a new block B, with B as parent, then if n is the length of the longest chain of descendants from B at that time, gravity, B, equals gravity, B, asterisk 0.99 n, note that values other than 0.99 can also be used. Essentially, we explicitly penalize forks that come later. S has the property that, unlike more naive approaches at subjectivity, it mostly avoids permanent network splits. If the time between the first node on the network hearing about block B and the last node on the network hearing about block B is an interval of k blocks, then a fork is unsustainable unless the lengths of the two forks remain forever within roughly k% of each other. If that is the case, then the differing gravities of the forks will ensure that half of the network will forever see one fork as higher scoring and the other half will support the other fork. Hence, S is weakly subjective with X roughly corresponding to how close to a 50/50ths network split the attacker can create, e.g. if the attacker can create a 70/30ths split, then X equals 0.29. In general, the max revert n blocks rule is superior and less complex, but S may prove to make more sense in situations where users are fine with high degrees of subjectivity, i.e. n being small, in exchange for a rapid ascent to very high degrees of security, i.e. immune to a 99% attack after n blocks. Consequences. So what would a world powered by weakly subjective consensus look like? First of all, nodes that are always online would be fine. In those cases, weak subjectivity is by definition equivalent to objectivity. Nodes that pop online once in a while, or at least once every n blocks, would also be fine, because they would be able to constantly get an updated state of the network. However, new nodes joining the network, and nodes that appear online after a very long time, would not have the consensus algorithm reliably protecting them. Fortunately, for them, the solution is simple. The first time they sign up, and every time they stay offline for a very, very long time, they need only get a recent block hash from a friend, a blockchain explorer, or simply their software provider, and paste it into their blockchain client as a checkpoint. They will then be able to securely update their view of the current state from there. This security assumption, the idea of getting a block hash from a friend, may seem unrigorous to many. Bitcoin developers often make the point that if the solution to long-range attacks is some alternative deciding mechanism X, then the security of the blockchain ultimately depends on X. And so the algorithm is in reality no more secure than using X directly, implying that most X, including our social consensus-driven approach, are insecure. However, this logic ignores why consensus algorithms exist in the first place. Consensus is a social process, and human beings are fairly good at engaging in consensus on our own without any help from algorithms. Perhaps the best example is the rice stones, where a tribe in Yap essentially maintained a blockchain recording changes to the ownership of stones, used as a Bitcoin-like zero intrinsic value asset, as part of its collective memory. The reason why consensus algorithms are needed is, quite simply, because humans do not have infinite computational power, and prefer to rely on software agents to maintain consensus for us. Software agents are very smart, in the sense that they can maintain consensus on extremely large states with extremely complex rule sets with perfect precision, but they are also very ignorant, in the sense that they have very little social information, and the challenge of consensus algorithms is that of creating an algorithm that requires as little input of social information as possible. Weak subjectivity is exactly the correct solution. It solves the long-range problems with proof of stake by relying on human-driven social information, but leaves to a consensus algorithm the role of increasing the speed of consensus from many weeks to 12 seconds and of allowing the use of highly complex rule sets in a large state. The role of human-driven consensus is relegated to maintaining consensus on block hashes over long periods of time, something which people are perfectly good at. A hypothetical oppressive government which is powerful enough to actually cause confusion over the true value of a block hash from 1 year ago would also be powerful enough to overpower any proof of work algorithm, or cause confusion about the rules of blockchain protocol. Note that we do not need to fix n. Theoretically, we can come up with an algorithm that allows users to keep their deposits locked down for longer than n blocks. And users can then take advantage of those deposits to get a much more fine-grained reading of their security level. For example, if a user has not logged in since t blocks ago, and 23% of deposits have term length greater than t, then the user can come up with their own subjective scoring function that ignores signatures with newer deposits, and thereby be secure against attacks with up to 11.5% of total stake. An increasing interest rate curve can be used to incentivize longer-term deposits over shorter ones, or for simplicity we can just rely on altruism prime. Marginal cost, the other objection. One objection to long-term deposits is that it incentivizes users to keep their capital locked up, which is inefficient, the exact same problem as proof of work. However, there are 4 counterpoints to this. First, marginal cost is not total cost, and the ratio of total cost divided by marginal cost is much less for proof of stake than proof of work. A user will likely experience close to no pain from locking up 50% of their capital for a few months, a slight amount of pain from locking up 70%, but would find locking up more than 85% intolerable without a large reward. Additionally, different users have very different preferences for how willing they are to lock up capital. Because of these two factors put together, regardless of what the equilibrium interest rate ends up being, the vast majority of the capital will be locked up at far below marginal cost. Second, locking up capital is a private cost, but also a public good. The presence of locked-up capital means that there is less money supply available for transactional purposes, and so the value of the currency will increase, redistributing the capital to everyone else, creating a social benefit. Third, security deposits are a very safe store of value, so, they substitute the use of money as a personal crisis insurance tool, and, 2, many users will be able to take out loans in the same currency collateralized by the security deposit. Finally, because proof of stake can actually take away deposits for misbehaving, and not just rewards, it is capable of achieving a level of security much higher than the level of rewards. Whereas in the case of proof of work the level of security can only equal the level of rewards. There is no way for a proof of work protocol to destroy misbehaving miners' ASICs. Fortunately, there is a way to test those assumptions. Launch a proof of stake coin with a stake reward of 1%, 2%, 3%, etc. per year, and see just how large a percentage of coins become deposits in each case. Users will not act against their own interests, so we can simply use the quantity of funds spent on consensus as a proxy for how much inefficiency the consensus algorithm introduces. If proof of stake has a reasonable level of security at a much lower reward level than proof of work, then we know that proof of stake is a more efficient consensus mechanism. And we can use the levels of participation at different reward levels to get an accurate idea of the ratio between total cost and marginal cost. Ultimately, it may take years to get an exact idea of just how large the capital lockup costs are. Altogether, we now know for certain that proof of stake algorithms can be made secure. And weak subjectivity is both sufficient and necessary as a fundamental change in the security model to sidestep nothing at stake concerns to accomplish this goal. And, 2, there are substantial economic reasons to believe that proof of stake actually is much more economically efficient than proof of work. Proof of stake is not an unknown. The past 6 months of formalization and research have determined exactly where the strengths and weaknesses lie, at least to as large extent as with proof of work, where mining centralization uncertainties may well forever abound. Now, it's simply a matter of standardizing the algorithms, and giving blockchain developers the choice. Ethereum is a notoriously adversarial environment.
And this is very
Ethereum
long,
has even been compared.
Let's do this one first. I think I'll do the documentation ones and then I'll go back to studying the code.
Merkle Patricia tree. Last edit at Wakaro, February 9, 2023. A Merkle Patricia tree provides a cryptographically authenticated data structure that can be used to store all key value bindings. Merkle Patricia tries are fully deterministic, meaning that tries with the same key value bindings is guaranteed to be identical down to the last byte. This means that they have the same root hash, providing the holy grail of O, log, n, efficiency for inserts, lookups, and deletes. Moreover, they are simpler to understand in code than more complex comparison-based alternatives, like red-black trees. Prerequisites. To better understand this page, it would be helpful to have basic knowledge of hashes, Merkle trees, tries and serialization. Basic radix tries. In a basic radix tree, every node looks as follows. 1 I0, I1, in, value 2. Where I0, in represent the symbols of the alphabet, often binary or hex, value is the terminal value at the node, and the values in the I0, I1, in slots are either null or pointers to, in our case, hashes of, other nodes. This forms a basic, key, value, store. Say you wanted to use a radix tree data structure for persisting an order over a set of key value pairs. To find the value currently mapped to the key dog in the tree, you would first convert dog into letters of the alphabet, giving 64 6F67, and then descend the tree following that path until you find the value. That is, you start by look up the root hash in a flat key /value db to find the root node of the tree. It is represented as an array of keys pointing to other nodes. You would use the value at index 6 as a key and look it up in the flat key /value db to get the node 1 level down. Then pick index 4 to look up the next value, then pick index 6, and so on, until, once you followed the path, root-6-4-6-15-6-7, you look up the value of the node and return the result. There is a difference between looking something up in the tree and the underlying flat key /value db. They both define key /values arrangements, but the underlying db can do a traditional one-step lookup of a key. Looking up a key in the tree requires multiple underlying db lookups to get to the final value described above. Let's refer to the latter as a path to eliminate ambiguity. The update and delete operations for radix tries can be defined as follows. 1 def update, node path value 2 if path equals 3 kernode equals db.get, node, if node else null asterisk 174 nunid equals kernode.copy, 5 nunid-1 equals value 6 else. 7 kernode equals db.get, node, if node else null asterisk 178 nunid equals kernode.copy, 9 new index equals update, kernode path 0 path 1 value, 10 nunid path 0 equals new index 11 db.put, hash, nunid. Nunid. 23 new, a Merkle radix tree is built by linking nodes using deterministically generated cryptographic hash digests. This content addressing, in the key /value db key equals cupcake 256, RLP, value, provides cryptographic authentication of the stored data. If the root hash of a given tree is publicly known, then anyone can provide a proof that the tree includes a given value at a specific path by providing the hashes of each node joining a specific value to the tree root. It is impossible for an attacker to provide a proof of a path, value, pair that does not exist since the root hash is ultimately based on all hashes below it. Any underlying modification would change the root hash. We'll refer to an atomic unit of a radix tree, e.g. a single hex character, or 4-bit binary number, as a nibble. While traversing a path 1 nibble at a time, as described above, nodes can maximally refer to 16 children but include a value element. We, hence, represent them as array with length. We call these 17-element arrays branch nodes. Merkle Patricia tree. Radix tries have one major limitation: they are inefficient. If you want to store one path value binding where the path, like in Ethereum, is 64 characters long, the number of nibbles in bytes 32. We will need over a kilobyte of extra space to store one level per character, and each lookup or delete will take the full 64 steps. The Patricia tree introduced in the following solves this issue. Optimization. A node in a Merkle Patricia tree is one of the following. Null, represented as the empty string. Branch a 17-item node v0, v15, vt. Leaf a 2-item node encoded path, value. Extension a 2-item node encoded path, key. With 64 character paths, it is inevitable that after traversing the first few layers of the tree, you will reach a node where no divergent path exists for at least part of the way down. To avoid having to create up to 15 sparse null nodes along the path, we shortcut the descent by setting up an extension node of the form encoded path, key. Where encoded path contains the partial path to skip ahead, using a compact encoding described below, and the key is for the next db lookup. For a leaf node, which can be marked by a flag in the first nibble of the encoded path, the path encodes all prior nodes' path fragments and we can look up the value directly. This above optimization, however, introduces ambiguity. When traversing paths in nibbles, we may end up with an odd number of nibbles to traverse, but because all data is stored in bytes format, it is not possible to differentiate between, for instance, the nibble 1 and the nibble 01, both must be stored as. To specify odd length, the partial path is prefixed with a flag. Specification, compact encoding of hex sequence with optional terminator. The flagging of both odd vs. Even remaining partial path length and leaf vs. Extension node as described above reside in the first nibble of the partial path of any 2-item node. They result in the following. 1 hex char bits node type partial path length 2 for even remaining path length 0 or 2. Another 0 padding nibble will always follow. 1 def compact encode hex array 2 term equals 1 if hex array -1 equals 16 else 0 3 if term hex array equals hex array :-1 4 auto len equals len 7 hex array 13 o plus examples 1 here is the extended code for getting a node in the Merkle Patricia tree. 1 def get helper node path 2 if path equals return node 3 if node equals return 4 kernode equals rlp.decode node if len node v2 equals kernode 7 k2 equals compact decode k2 8 if k2 equals path len k2 9 return get v2 path len k2 10 else 11 return 12 if len kernode equals 17 13 return get helper kernode path 0 path 1 14 15 def get node path 16 path 2 equals 17 for I in range len path 18 path 2 dot push int ord path I /16 19 path 2 dot push ord path I %16 20 path 2 dot push 16 21 return get helper node path 2 22 show all. Example tree. Suppose we want a tree containing 4 path/value pairs, do, verb, dog, puppy, doge, coin, horse, stallion. First, we convert both paths and values to bytes. Below, actual byte representations for paths are denoted by, although values are still shown as strings, denoted by, for easier comprehension, they, too, would actually be bytes. 1, verb 2, puppy 3, coin 4, Now, we build such a tree with the following key/value pairs in the underlying DB. 1 root hash, hashy. When one node is referenced inside another node, what is included is h, rlp.encode, x, where h, x, equals cake 256, x, if len, x, equals 32 else x and rlp.encode is the RLP encoding function. Note that when updating a tree, one needs to store the key/value pair, cake 256, x, x, in a persistent lookup table if the newly created node has length equals 32. However, if the node is shorter than that, one does not need to store anything, since the function f, x, equals x is reversible. Tries in Ethereum. All of the Merkle tries in Ethereum's execution layer use a Merkle Patricia tree. From a block header there are 3 roots from 3 of these tries. State root, transactions root, receipts root, state tree. There is one global state tree, and it is updated every time a client processes a block. In it, a path is always, cake 256, Ethereum address, and a value is always, RLP, Ethereum account. More specifically, an Ethereum account is a 4-item array of nonce-balanced storage root code hash. At this point, it's worth noting that this storage root is the root of another Patricia tree. Storage tree. Storage tree is where all contract data lives. There is a separate storage tree for each account. To retrieve values at specific storage positions at a given address, the storage address, integer position of the stored data in the storage, and the block ID are required. These can then be passed as arguments to the ethget storage at defined in the JSON RPC API, e.g. to retrieve the data in storage slot 0 for address 0x295A70B, 1 curl x post data. Result col. Retrieving other elements in storage is slightly more involved because the position in the storage tree must first be calculated. The position is calculated as the cake 256 hash of the address and the storage position, both left padded with zeros to a length of 32 bytes. For example, the position for the data in storage slot 1 in a geth console, this can be calculated as follows. Hex, the path is therefore cake 256. This can now be used to retrieve the data from the storage tree as before. 1 latest, transactions tree. There is a separate transactions tree for every block, again storing, key, value, pairs. A path here is, RLP, transaction index, which represents the key that corresponds to a value determined by 1 if legacy tx2 value equals RL. More information on this can be found in the EIP2 receipts tree. Every block has its own receipts tree. A path here is, RLP, transaction index. Transaction index is its index within the block it's mined. The receipts tree is never updated. Similar to the transactions tree, there are current and legacy receipts. To query a specific receipt in the receipts tree, the index of the transaction in its block, the receipt payload and the transaction type are required. The returned receipt. More information on this can be found in the EIP 2718 documentation. Further reading. Recursive length prefix, RLP, serialization. Last edit at Lou Alex, January 7, 2023. Recursive length prefix, RLP, serialization is used extensively in Ethereum's execution clients. RLP standardizes the transfer of data between nodes in a space-efficient format. The purpose of RLP is to encode arbitrarily nested arrays of binary data, and RLP is the primary encoding method used to serialize objects in Ethereum's execution layer. The only purpose of RLP is to encode structure. Encoding specific data types, e.g. strings, floats, is left up to higher order protocols. But positive RLP integers must be represented in big-endian binary form with no leading zeros, thus making the integer value 0 equivalent to the empty byte array. Deserialized positive integers with leading zeros get treated as invalid. The integer representation of string length must also be encoded this way, as well as integers in the payload. More information in the Ethereum Yellow Paper, Appendix B. To use RLP to encode a dictionary, the 2 suggested canonical forms are: use K1v1, K2v2, with keys in lexicographic order. Use the higher level Patricia tree encoding as Ethereum does. Definition. The RLP encoding function takes in an item. An item is defined as follows. A string, i.e. byte array, is an item. A list of items is an item. For example, all of the following are items. An empty string. The string containing the word cat. A list containing any number of strings. And a more complex data structures like cat, puppy, cow, horse, pig, sheep. Note that in the context of the rest of this page, string means a certain number of bytes of binary data.
I think I'm gonna put the other headsets while, not headset, the phone, while I read the stuff. And I think I'm probably gonna read this parts of the documentation. I'm gonna read the Gasper as well. So this one, this shoe here, and then the Gasper, and then I'll probably read the Ethereum Yellow Paper after that. Not sure how long it's gonna take, but probably 1 hour or something like that. And then I'm probably gonna study the source code after that. Not really sure if I should study now or later. It's kind of hard to decide because there's so much code. I'm worried that if I study it right away, it's gonna be too difficult to understand how everything's connected. So I'm trying to, especially the parts of uncle blocks and the mempool. That stuff is the hardest to wrap my mind around. It's hard to understand, like in the context of everything how were the things designed in the protocol. And with ChatGPT is difficult as well because ChatGPT is still on the version, like the proof of stake was done after ChatGPT stopped, after they ran or they trained ChatGPT. So there might be a conflict there in the information. But after I realized that the ChatGPT wasn't giving me the wrong commands, was just giving me folders that were not inside of the P2P. So this one is an example. So it was describing the folders correctly. Yeah, I'm gonna read the articles first, the documentation first, and then I'll start studying the source code. So I'm gonna change the font.
Note that in the context of the rest of this page, string means a certain number of bytes of binary data, no special encodings are used, and no knowledge about the content of the strings is implied. RLP encoding is defined as follows. For a single byte whose value is in the 0x00, 0x7f, decimal 0, 127 range, that byte is its own RLP encoding. Otherwise, if a string is 0 to 55 bytes long, the RLP encoding consists of a single byte with value 0x80, December 128, plus the length of the string followed by the string. The range of the first byte is thus 0x80, 0xb7, December 128, 100. If a string is more than 55 bytes long, the RLP encoding consists of a single byte with value 0xb7, December 183, plus the length in bytes of the length of the string in binary form, followed by the length of the string, followed by the string. For example, a 1024-byte long string would be encoded as \xb9\x04\x0 185. Here, 0xb9, 183 plus 2 equals 185. 1024, that denote the length of the actual string. The range of the first byte is thus 0xb8. If the total payload of a list, i.e. the combined length of all its items being RLP encoded, is 0 to 55 bytes long, the RLP encoding consists of a single byte with value 0xc0 plus the length of the list followed by the concatenation. If the total payload of a list is more than 55 bytes long, the RLP encoding consists of a single byte with, followed by the length of the payload, followed by the concatenation of the RLP encodings of the items. The range of the first byte is thus 0xf8, 0xff, December 248, 255. Encode, this is 14BL equals tobinary, L, 15 return CHR, len, examples. The string dog equals 0x83, D, O, G. The list cat, dog equals 0xc8, 0. The list cat, dog equals 0xc8, 0x83, C, A, T, 0x83, D, O, G. The empty string, null, equals 0x80. The empty list equals 0xc0. The integer 0 equals 0x80. RLP decoding. According to the rules and process of RLP encoding, the input of RLP decode is regarded as an array of binary data. The RLP decoding process is as follows. According to the first byte, i.e. prefix, of input data and decoding the data type, the length of the actual data and offset. According to the type and offset of data, decode the data correspondingly. Continue to decode the rest of the input. Among them, the rules of decoding data types and offset is as follows. The data is a string if the range of the first byte, i.e. prefix, is 0x00, 0x7f, and the string is the first byte itself exactly. The data is a string if the range of the first byte is 0x80, 0xb7, and the string whose length is equal to the first byte minus 0x80 follows the first byte. The data is a string if the range of the first byte is 0xb8, 0xbf, and the length of the string whose length in bytes is equal to the first byte minus 0xb7 follows the first byte, and the string follows the length of the string. The data is a list if the range of the first byte is 0xc0, 0xf7, and the concatenation of the RLP encodings of all items. The data is a list if the range of the first byte is 0. 42 return ord, B. The data is a list if the range of the first byte is 0xf8, 0xff, and the total payload of the list whose length, and the concatenation of the RLP encodings of all items of the list follows the total payload of the list. Node architecture. Last edit at Petnerub, January 16, 2023. An Ethereum node is composed of two clients, an execution client and a consensus client. When Ethereum was using proof of work, an execution client was enough to run a full Ethereum node. However, since implementing proof of stake, the execution client needs to be used alongside another piece of software called a consensus client. The diagram below shows the relationship between the two Ethereum clients. The two clients connect to their own respective peer-to-peer, P2P, networks. Separate P2P networks are needed as the execution clients gossip transactions over their P2P network, enabling them to manage their local transaction pool, whilst the consensus clients gossip blocks over their P2P network, enabling consensus and chain growth. This image is borrowed from geth.ethereum.org and uses the Geth logo to represent execution clients. There are other options for the execution client including Aragon, Nethermind, and Bisu. For this two-client structure to work, consensus clients must be able to pass bundles of transactions to the execution client. Executing the transactions locally is how the client validates that the transactions do not violate any Ethereum rules and that the proposed update to Ethereum's state is correct. Likewise, when the node is selected to be a block producer, the consensus client must be able to request bundles of transactions from Geth to include in the new block and execute them to update the global state. This inter-client communication is handled by a local RPC connection using the Engine API. What does the execution client do? The execution client is responsible for transaction handling, transaction gossip, state management and supporting the Ethereum virtual machine, EVM. However, it is not responsible for block building, block gossiping or handling consensus logic. These are in the remit of the consensus client. The execution client creates execution payloads, the list of transactions, updated state tree, and other execution-related data. Consensus clients include the execution payload in every block. The execution client is also responsible for re-executing transactions in new blocks to ensure they are valid. Executing transactions is done on the execution client's embedded computer, known as the Ethereum virtual machine, EVM. The execution client also offers a user interface to Ethereum through RPC methods that enable users to query the Ethereum blockchain, submit transactions, and deploy smart contracts. It's common for RPC calls to be handled by a library like Web3.js, Web3.py, or by a user interface such as a browser wallet. In summary, the execution client is a user gateway to Ethereum, home to the Ethereum virtual machine, Ethereum state, and transaction pool. What does the consensus client do? The consensus client deals with all the logic that enables a node to stay in sync with the Ethereum network. This includes receiving blocks from peers and running a fork choice algorithm to ensure the node always follows the chain with the greatest accumulation of attestations, weighted by validator effective balances. Similar to the execution client, consensus clients have their own P2P network through which they share blocks and attestations. The consensus client does not participate in attesting to or proposing blocks. This is done by a validator, an optional add-on to a consensus client. A consensus client without a validator only keeps up with the head of the chain, allowing the node to stay synced. This enables a user to transact with Ethereum using their execution client, confident that they are on the correct chain. Validators. Node operators can add a validator to their consensus clients if 32ETH is the deposit contract. The validator client comes bundled with the consensus client and can be added to a node at any time. The validator handles attestations and block proposals. They enable a node to accrue rewards or lose ETH via penalties or slashing. Running the validator software also makes a node eligible to be selected to propose a new block. Components of a node comparison. Execution client consensus client validator gossips transactions over its P2P network gossips blocks and attestations over its P2P network proposes nodes and clients. Last edit at Corwin Times, Ethereum is a distributed network of computers, known as nodes, running software that can verify blocks and transaction data. The software application, known as a client, must be run on your computer to turn it into an Ethereum node. Note, it is not possible to run an execution client on its own anymore. After the merge, both execution and consensus clients must be run together in order for a user to gain access to the Ethereum network. Prerequisites. You should understand the concept of a peer-to-peer network and the basics of the EVM before diving deeper and running your own instance of an Ethereum client. Take a look at our introduction to Ethereum. If you are new to the topic of nodes, we recommend what are nodes and clients. A node is any instance of Ethereum client software that is connected to other computers also running Ethereum software, forming a network. A client is an implementation of Ethereum that verifies data against the protocol rules and keeps the network secure. Post-merge Ethereum consists of two parts, the execution layer and the consensus layer. Both layers are run by different client software. On this page, we'll refer to them as the execution client and consensus client. The execution client, also known as the execution engine, L client, or formerly the ETH1 client, listens to new transactions broadcasted in the network, executes them in EVM, and holds the latest state and database of all current Ethereum data. The consensus client, also known as the beacon node, CL client, or formerly the ETH2 client, implements the proof-of-stake consensus algorithm, which enables the network to achieve agreement based on validated data from the execution client. Before the merge, consensus and execution layer were separate networks, with all transactions and user activity on the Ethereum happening at what is now the execution layer. One client software provided both execution environment and consensus verification of blocks produced by miners. The consensus layer, the beacon chain, has been running separately since December 2020. It introduced proof-of-stake and coordinated the network of validators based on data from the Ethereum network. With the merge, Ethereum transitions to proof-of-stake by connecting these networks. Execution and consensus clients work together to verify Ethereum's state. Modular design with various software pieces working together is called encapsulated complexity. This approach makes it easier to execute the merge seamlessly and enables the reuse of individual clients, for example, in the Layer 2 ecosystem. Simplified diagram. Simplified diagram of a coupled execution and consensus client. Client diversity. Both execution clients and consensus clients exist in a variety of programming languages developed by different teams. Multiple client implementations can make the network stronger by reducing its dependency on a single code base. The ideal goal is to achieve diversity without any client dominating the network, thereby eliminating a potential single point of failure. The variety of languages also invites a broader developer community and allows them to create integrations in their preferred language. Learn more about client diversity. What these implementations have in common is they all follow a single specification. Specifications dictate how the Ethereum network and blockchain functions. Every technical detail is defined in tracking nodes in the network. Multiple trackers offer a real-time overview of nodes in the Ethereum network. Note that due to the nature of decentralized networks, these crawlers can only provide a limited view of the network and might report different results. Map of nodes by Etherscan. Ether nodes by Bitfly. Ethereum node crawler. Node types. If you want to run your own node, you should understand that there are different types of node that consume data differently. In fact, clients can run 3 different types of nodes: light, full, and archive. There are also options of different sync strategies which enable faster synchronization time. Synchronization refers to how quickly it can get the most up-to-date information on Ethereum's state. Full node. Stores full blockchain data, although this is periodically pruned so a full node does not store all state data back to Genesis. Participates in block validation, verifies all blocks and states. All states can be derived from a full node, although very old states are reconstructed from requests made to archive nodes. Light node. Instead of downloading every block, light nodes download block headers. These headers only contain summary information about the contents of the blocks. Any other information required by the light node gets requested from a full node. The light node can then independently verify the data they receive against the state roots in the block headers. Light nodes enable users to participate in the Ethereum network without the powerful hardware or high bandwidth required to run full nodes. Eventually, light nodes might run on mobile phones or embedded devices. The light nodes do not participate in consensus, i.e. they cannot be miners/validators, but they can access the Ethereum blockchain with the same functionality and security guarantees as a full node. The execution client Geth includes a light sync option. However, a light Geth node relies upon full nodes serving light node data. Few full nodes opt to serve light node data. Light clients are an area of active development for Ethereum, and we expect to see new light clients for the consensus layer and execution layer soon. There are also potential routes to providing light client data over the Gossip network. This is advantageous because the Gossip network could support a network of light nodes without requiring full nodes to serve requests. Ethereum does not support a large population of light nodes yet, but light node support is an area expected to develop rapidly in the near future. In particular, archive node stores everything kept in the full node and builds an archive of historical states. It is needed if you want to query something like an account balance at block number 4 million, or simply and reliably test your own transactions set without mining them using tracing. This data represents units of terabytes, which makes archive nodes less attractive for average users but can be handy for services like block explorers, wallet vendors, and chain analytics. Syncing clients in any mode other than archive will result in pruned blockchain data. This means, there is no archive of all historical states, but the full node is able to build them on demand. Learn more about archive nodes. Why should I run an Ethereum node? Running a node allows you to directly, trustlessly, and privately use Ethereum while supporting the network by keeping it more robust and decentralized. Benefits to you. Running your own node enables you to use Ethereum in a private, self-sufficient, and trustless manner. You don't need to trust the network because you can verify the data yourself with your client. Don't trust, verify is a popular blockchain mantra. Your node verifies all the transactions and blocks against consensus rules by itself. This means you don't have to rely on any other nodes in the network or fully trust them. You can use an Ethereum wallet with your own node. You can use dApps more securely and privately because you won't have to leak your addresses and balances to random nodes. Everything can be checked with your own client. MetaMask, Frame, and many other wallets offer RPC importing, allowing them to use your node. You can run and self-host other services which depend on data from Ethereum. For example, this might be a beacon chain validator, software like Layer 2, infrastructure, block explorers, payment process. You can provide your own custom RPC endpoints. Publicly for the community or even privately hosted Ethereum endpoint enables people to use your node and avoid big centralized providers. You can connect to your node using inter-process communications, IPC, or rewrite the node to load your program as a plugin. This grants low latency, which helps a lot, e.g. when processing a lot of data using Web3 libraries or when you need to replace your transactions as fast as possible, i.e. front running. You can directly stake ETH to secure the network and earn rewards. You can directly stake ETH to secure the network and earn rewards. See solo staking to get started. Network benefits. A diverse set of nodes is important for Ethereum's health, security, and operational resiliency. Full nodes enforce the consensus rules so they can't be tricked into accepting blocks that don't follow them. This provides extra security in the network because if all the nodes were light nodes, which don't do full verification, validators could attack the network. In case of an attack which overcomes the crypto-economic defenses of proof of stake, a social recovery can be performed by full nodes choosing to follow the honest chain. More nodes in the network result in a more diverse and robust network, the ultimate goal of decentralization, which enables a censorship-resistant and reliable system. They provide access to blockchain data for lightweight clients that depend on it. In high peaks of usage, there need to be enough full nodes to help light nodes sync. Light nodes don't store the whole blockchain, instead they verify data via the state roots in block headers. They can request more information from blocks if they need it. If you run a full node, the whole Ethereum network benefits from it, running your own node. Interested in running your own Ethereum client? For a beginner-friendly introduction, visit our Run a Node alternatives. Setting up your own node can cost you time and resources, but you don't always need to run your own instance. In this case, you can use a third-party API provider like Infura, Alchemy, Chainstack, QuickNode, Tenderly, Blast. Alternatively, Archive Node is a community-funded archive node that hopes to bring archive data on the Ethereum blockchain to independent developers who otherwise couldn't afford it. For an overview of using these services, check out Nodes as a Service. If somebody runs an Ethereum node with a public API in your community, you can point your light wallets, like MetaMask, to a community node via custom RPC and gain more privacy than with some random trusted third party. On the other hand, if you run a client, you can share it with your friends who might need it. Execution clients, formerly ETH1 clients. The Ethereum community maintains multiple open-source execution clients, previously known as ETH1 clients, or just Ethereum clients, developed by different teams using different programming languages. This makes the network stronger and more diverse. The ideal goal is to achieve diversity without any client dominating to reduce any single points of failure. This table summarizes the different clients. All of them pass client tests and are actively maintained to stay updated with network upgrades. Client language operating systems network sync. Note that Open Ethereum has been deprecated and is no longer being maintained. Use another client implementation. For more on supported networks, read up on Ethereum networks. Each client has unique use cases and advantages, so you should choose one based on your own preferences. Diversity allows implementations to be focused on different features and user audiences. You may want to choose a client based on features, support, programming language, or licenses. Bisu. Hyperledger Bisu is an enterprise-grade Ethereum client for public and permissioned networks. It runs all of the Ethereum mainnet features, from tracing to GraphQL, has extensive monitoring and is supported by consensus, both in open community channels and through commercial SLAs for enterprises. It is written in Java and is Apache 2. Bisu's extensive documentation will guide you through all details on its features and setups. Aragon. Aragon, formerly known as TurboGeth, started as a fork of Go Ethereum oriented toward speed and disk space efficiency. Aragon is a completely re-architected implementation of Ethereum. Nethermind is an Ethereum implementation created with the C#.NET tech stack, licensed with LGPL 3.0, running on all major platforms including ARM. It offers great performance with an optimized virtual machine, state access, networking and rich features like Prometheus/Grafana dashboards, SEC enterprise logging support, JSON RPC tracing, and analytics plugins. Nethermind also has detailed documentation, strong dev support, an online community and 20 consensus clients, formerly ETH2 clients. There are multiple consensus clients, previously known as ETH2 clients, to support the consensus upgrades. They are running the beacon chain and will provide a proof-of-stake consensus mechanism to execution clients after the merge. Lighthouse. Lighthouse is a consensus client implementation written in Rust under the Apache 2.0 license. It is maintained synchronization modes. To follow and verify current data in the network, the Ethereum client needs to sync with the latest network state. This is done by downloading data from peers, cryptographically verifying their integrity, and building a local blockchain database. Synchronization modes represent different approaches to this process with various trade-offs. Clients also vary in their implementation of sync algorithms. Always refer to the official documentation of your chosen client for specifics on implementation. Execution layer sync modes. Full sync. Full sync downloads all blocks, including headers, transactions, and receipts, and generates the state of the blockchain incrementally by executing every block from Genesis. Minimizes trust and offers the highest security by verifying every transaction. With an increasing number of transactions, it can take days to weeks to process all transactions. Fast sync. Fast sync downloads all blocks, including headers, transactions, and receipts, verifies all headers, downloads the state and verifies it against the headers. Relies on the security of the consensus mechanism. Synchronization takes only a few hours. Light sync. Light client mode downloads all block headers, block data, and verifies some randomly. Only syncs tip of the chain from the trusted checkpoint. Gets only the latest state while relying on trust in developers and consensus mechanism. Client ready to use with current network state in a few minutes. NB Lightsync does not yet work with proof. SnapSync. SnapSync is the latest approach to syncing a client, pioneered by the Geth team. Using dynamic snapshots served by peers retrieves all the account and storage data without downloading intermediate tree nodes and then reconstructs the Merkle tree locally. Fastest sync strategy, currently default in Ethereum mainnet. Saves a lot of disk usage and network bandwidth without sacrificing security. More on SnapSync. Consensus layer sync modes. Optimistic sync. Optimistic sync is a post-merge synchronization strategy designed to be opt-in and backwards compatible, allowing execution nodes to sync via established methods. The execution engine can optimistically import beacon blocks without fully verifying them, find the latest head, and then start syncing the chain with the above methods. Then, after the execution client has caught up, it will inform the consensus client of the validity of the transactions in the beacon chain. More on optimistic sync. Checkpoint sync. Checkpoint sync, also known as weak subjectivity sync, creates a superior user experience for syncing beacon node. It's based on assumptions of weak subjectivity which enables syncing beacon chain from a recent weak subjectivity checkpoint instead of Genesis. Checkpoint sync makes the initial sync time significantly faster with similar trust assumptions as syncing from Genesis. In practice, this means your node connects to a remote service to download recent finalized states and continues verifying data from that point. Third party providing the data is trusted and should be picked carefully. More on checkpoint sync. Further reading. There is a lot of information about Ethereum clients on the internet. Here are a few resources that might be helpful. Ethereum 101, Part 2, Understanding Nodes, Will Barnes, February 13, 2019. Running Ethereum Full Nodes, A Guide for the Barely Motivated, Justin LaRue, November 7, 2019. Related topics. Blocks. Networks. Related tutorials. Turn your Raspberry Pi 4 into a validator node just by flashing the microSD card. Encapsulated vs Systemic Complexity in Protocol Design. 2022 February 28. One of the main goals of Ethereum protocol design is to minimize complexity, make the protocol as simple as possible, while still making a blockchain that can do what an effective blockchain needs to do. The Ethereum protocol is far from perfect at this, especially since much of it was designed in 2014 to 16 when we understood much less, but we nevertheless make an active effort to reduce complexity whenever possible. One of the challenges of this goal, however, is that complexity is difficult to define, and sometimes, you have to trade off between two choices that introduce different kinds of complexity and have different costs. How do we compare? One powerful intellectual tool that allows for more nuanced thinking about complexity is to draw a distinction between what we will call encapsulated complexity and systemic complexity. Encapsulated complexity occurs when there is a system with subsystems that are internally complex, but that present a simple interface to the outside. Systemic complexity occurs when the different parts of a system can't even be cleanly separated, and have complex interactions with each other. Here are a few examples. BLS signatures vs Schnorr signatures. BLS signatures and Schnorr signatures are two popular types of cryptographic signature schemes that can be made with elliptic curves. BLS signatures appear mathematically very simple. Signing, sigma equals H, M, K. Verifying, E, 1 sigma, equals, E, H, M, K. H is a hash function, M is the message, and K are the private and public keys. So far, so simple. However, the true complexity is hidden inside the definition of the E function, elliptic curve pairings, one of the most devilishly hard to understand pieces of math in all of cryptography. Now, consider Schnorr signatures. Schnorr signatures rely only on basic elliptic curves. But the signing and verification logic is somewhat more complex. So, which type of signature is simpler? It depends what you care about. BLS signatures have a huge amount of technical complexity, but the complexity is all buried within the definition of the E function. If you treat the E function as a black box, BLS signatures are actually really easy. Schnorr signatures, on the other hand, have less total complexity, but they have more pieces that could interact with the outside world in tricky ways. For example, doing a BLS multi-signature, a combined signature from two keys K1 and K2, is easy, just take sigma 1 plus sigma 2. But a Schnorr multi-signature requires 2 rounds of interaction, and there are tricky key cancellation attacks that need to be dealt with. Schnorr signatures require random number generation, BLS signatures do not. Elliptic curve pairings in general are a powerful, complexity sponge in that they contain large amounts of encapsulated complexity, but enable solutions with much less systemic complexity. This is also true in the area of polynomial commitments. Compare the simplicity of KZG commitments, which require pairings, to the much more complicated internal logic of inner product arguments, which do not. Cryptography vs cryptoeconomics. One important design choice that appears in many blockchain designs is that of cryptography versus cryptoeconomics. Often, e.g. in rollups, this comes in the form of a choice between validity proofs, aka ZK snarks, and fraud proofs. ZK snarks are complex technology. While the basic ideas behind how they work can be explained in a single post, actually implementing a ZK snark to verify some computation involves many times more complexity than the computation itself, hence why ZK snarks for the EVM are still under development while fraud proofs for the EVM are already in the testing stage. Implementing a ZK snark effectively involves circuit design with special purpose optimization, working with unfamiliar programming languages, and many other challenges. Fraud proofs, on the other hand, are inherently simple. If someone makes a challenge, you just directly run the computation on-chain. For efficiency, a binary search scheme is sometimes added, but even that doesn't add too much complexity. But while ZK snarks are complex, their complexity is encapsulated complexity. The relatively light complexity of fraud proofs, on the other hand, is systemic. Here are some examples of systemic complexity that fraud proofs introduce. They require careful incentive engineering to avoid the verifier's dilemma. If done in consensus, they require extra transaction types for the fraud proofs, along with reasoning about what happens if many actors compete to submit a fraud proof at the same time. They depend on a synchronous network. They allow censorship attacks to be also used to commit theft. Rollups based on fraud proofs require liquidity providers to support instant withdrawals. For these reasons, even from a complexity perspective, purely cryptographic solutions based on ZK snarks are likely to be long-run safer. ZK snarks have more complicated parts that some people have to think about, but they have fewer dangling caveats that everyone has to think about. Miscellaneous examples. Proof of work, Nakamoto consensus, low encapsulated complexity, as the mechanism is extremely simple and easy to understand, but higher systemic complexity, e.g. selfish mining attacks. Hash functions, high encapsulated complexity, but very easy to understand properties, so low systemic complexity. Random shuffling algorithms. Shuffling algorithms can either be internally complicated, as in Whisk, but lead to easy to understand guarantees of strong randomness. Or internally simpler but lead to randomness properties that are weaker and more difficult to analyze, systemic complexity. Miner extractable value, MEV, a protocol that is powerful enough to support complex transactions can be fairly simple internally. But those complex transactions can have complex systemic effects on the protocol's incentives by contributing to the incentive to propose blocks in very irregular ways. Verkle trees. Verkle trees do have some encapsulated complexity, in fact quite a bit more than plain Merkle hash trees. Systemically, however, Verkle trees present the exact same relatively clean and simple interface of a key-value map. The main systemic complexity leak is the possibility of an attacker manipulating the tree to make a particular value have a very long branch, but this risk is the same for both Verkle trees and Merkle trees. How do we make the trade-off? Often, the choice with less encapsulated complexity is also the choice with less systemic complexity, and so there is one choice that is obviously simpler. But at other times, you have to make a hard choice between one type of complexity and the other. What should be clear at this point is that complexity is less dangerous if it is encapsulated. The risks from complexity of a system are not a simple function of how long the specification is. A small 10-line piece of the specification that interacts with every other piece adds more complexity than a 100-line function that is otherwise treated as a black box. However, there are limits to this approach of preferring encapsulated complexity. Software bugs can occur in any piece of code, and as it gets bigger the probability of a bug approaches 1. Sometimes, when you need to interact with a subsystem in an unexpected and new way, complexity that was originally encapsulated can become systemic. One example of the latter is Ethereum's current two-level state tree, which features a tree of account objects, where each account object in turn has its own storage tree. This tree structure is complex, but at the beginning the complexity seemed to be well encapsulated. The rest of the protocol interacts with the tree as a key/value store that you can read and write to, so we don't have to worry about how the tree is structured. Later, however, the complexity turned out to have systemic effects. The ability of accounts to have arbitrarily large storage trees meant that there was no way to reliably expect a particular slice of the state, e.g. all accounts starting with 0x1234, to have a predictable size. This makes it harder to split up the state into pieces, complicating the design of syncing protocols in attempts to distribute the storage process. Why did encapsulated complexity become systemic? Because the interface changed. The fix? The current proposal to move to Verkle trees also includes a move to a well-balanced single-layer design for the tree. Ultimately, which type of complexity to favor in any given situation is a question with no easy answers. The best that we can do is to have an attitude of moderately favoring encapsulated complexity, but not too much, and exercise our judgment in each specific case. Sometimes, a sacrifice of a little bit of systemic complexity to allow a great reduction of encapsulated complexity really is the best thing to do. And other times, you can even misjudge what is encapsulated and what isn't. Each situation is different. The current proposal to move to Verkle trees also includes a move to a well-balanced single-layer design for the tree. An approximate introduction to how ZK snarks are possible. 2021 January 26th. Special thanks to Dang Krad Feist, Carl Floersk and Xiaowei Wang for feedback and review. Perhaps the most powerful cryptographic technology to come out of the last decade is general-purpose succinct zero-knowledge proofs, usually called ZK snarks, zero-knowledge succinct arguments of knowledge. A ZK snark allows you to generate a proof that some computation has some particular output, in such a way that the proof can be verified extremely quickly even if the underlying computation takes a very long time to run. The ZK, zero-knowledge, part adds an additional feature: the proof can keep some of the inputs to the computation hidden. For example, you can make a proof for the statement, I know a secret number, such that if you take the word cow, add the number to the end, and SHA-256 hash it 100 million times, the output starts with 0x57D00485AA. The verifier can verify the proof far more quickly than it would take for them to run 100 million hashes themselves, and the proof would also not reveal what the secret number is. In the context of blockchains, this has two very powerful applications. Scalability: if a block takes a long time to verify, one person can verify it and generate a proof, and everyone else can just quickly verify the proof instead. Privacy: you can prove that you have the right to transfer some asset, you received it, and you didn't already transfer it, without revealing the link to which asset you received. This ensures security without unduly leaking information about who is transacting with whom to the public. But ZK snarks are quite complex. Indeed, as recently as in 2014 to 17 they were still frequently called moon math. The good news is that since then, the protocols have become simpler and our understanding of them has become much better. This post will try to explain how ZK snarks work, in a way that should be understandable to someone with a medium level of understanding of mathematics. Note that we will focus on scalability. Privacy for these protocols is actually relatively easy once the scalability is there, so we will get back to that topic at the end. Why ZK snarks should be hard. Let us take the blocks. Last edited at Wakaro, September 29. Blocks are batches of transactions with a hash of the previous block in the chain. This links blocks together, in a chain, because hashes are cryptographically derived from the block data. This prevents fraud, because one change in any block in history would invalidate all the following blocks as all subsequent hashes would change and everyone running the blockchain would notice. Prerequisites. Blocks are a very beginner-friendly topic. But to help you better understand this page, we recommend you first read accounts, transactions, and our introduction to Ethereum. Why blocks? To ensure that all participants on the Ethereum network maintain a synchronized state and agree on the precise history of transactions, we batch transactions into blocks. This means dozens, or hundreds, of transactions are committed, agreed on, and synchronized all at once. Diagram adapted from Ethereum EVM illustrated. By spacing out commits, we give all network participants enough time to come to consensus, even though transaction requests occur dozens of times per second. Blocks are only created and committed on Ethereum once every 12 seconds. How blocks work. To preserve the transaction history, blocks are strictly ordered. Every new block created contains a reference to its parent block, and transactions within blocks are strictly ordered as well. Except in rare cases, at any given time, all participants on the network are in agreement on the exact number and history of blocks, and are working to batch the current live transaction requests into the next block. Once a block is put together by some validator on the network, it is propagated to the rest of the network. All nodes add this block to the end of their blockchain, and a new validator is selected to create the next block. The exact block assembly process and commitment/consensus process is currently specified by Ethereum's proof-of-stake protocol. Proof-of-stake protocol. Proof-of-stake means the following. Validating nodes have to stake 32 ETH into a deposit contract as collateral against bad behavior. This helps protect the network because provably dishonest activity leads to some or all of that stake being destroyed. In every slot, spaced 12 seconds apart, a validator is randomly selected to be the block proposer. They bundle transactions together, execute them and determine a new state. They wrap this information into a block and pass it around to other validators. Other validators who hear about a new block re-execute the transactions to ensure they agree with the proposed change to the global state. Assuming the block is valid, they add it to their own database. If a validator hears about two conflicting blocks for the same slot, they use their fork choice algorithm to pick the one supported by the most staked ETH. More on proof of stake. What's in a block? There is a lot of information contained within a block. At the highest level, a block contains the following fields. Field description slot the block belongs top proposer indexed ID of the validator proposing the block parent truth hash of the preceding block state truth root hash of the state object body and object containing several fields, as defined below. The block body contains several fields of its own. Field description randa revi ala value used to select the next block proposer with one data information about the deposit contract graphish arbitrary data used to tag blocks proposer /list of validators. To be slash attester slashings list of validators to be slash attestations list of attestations in favor of the current block deposits list of new deposits to the deposit contract voluntary exits list of validators exiting the network's aggregate subset of validators used to serve like clients execution payload transactions passed from the execution client. The attestations field contains a list of all the attestations in the block. Attestations have their own data type that contains several pieces of data. Each attestation contains field description aggregation bits, a list of which validators participated in this attestation data container with multiple subfields as I nature aggregate signature of all attesting validators. The data field in the attestation contains the following. Field description slot the attestation relates to index indices for attesting validators beacon block with root hash of the beacon block containing this object source at the last justified checkpoint target's latest epoch boundary block. Executing the transactions in the execution payload updates the global state. All clients re-execute the transactions in the execution payload to ensure the new state matches that in the new block state root field. This is how clients can tell that a new block is valid and safe to add to their blockchain. The execution payload itself is an object with several fields. There is also an execution payload header that contains important summary information about the execution data. These data structures are organized as follows. The execution payload header contains the following fields. Field description hash of the parent block, the recipient account address for paying transaction fees, toasted root hash for the global state after applying changes in this block, receipts of the transaction receipts tree, Bloom data structure containing event logs, pre-rain value used in random validator selection block, number of the current. The execution payload itself contains the following. Notice this is identical to the header except that instead of the root hash of the transactions it includes the actual list of transactions. Field description hash of the parent block, the recipient account address for paying block time. Block time refers to the time separating blocks. In Ethereum, time is divided up into 12-second units called slots. In each slot a single validator is selected to propose a block. Assuming all validators are online and fully functional, there will be a block in every slot, meaning the block time is 12s. However, occasionally validators might be offline when called to propose a block, meaning slots can sometimes go empty. This is different to proof-of-work-based systems where block times are probabilistic and tuned by the mining difficulty. Block size. A final important note is that blocks themselves are bounded in size. Each block has a target size of 15 million gas, but the size of blocks will increase or decrease in accordance with network demands, up until the block limit of 30 million gas, 2x target block size. The total amount of gas expended by all transactions in the block must be less than the block gas limit. This is important because it ensures that blocks can't be arbitrarily large. If blocks could be arbitrarily large, then less performant full nodes would gradually stop being able to keep up with the network due to space and speed requirements. The larger the block, the greater the computing power required to process them in time for the next slot. This is a centralizing force, which is resisted by capping block sizes. Further reading. Know of a community resource that helped you? Edit this page and add it. Related topics. Networks. Last edit at Corwin Tynes, February. Networks are different Ethereum environments you can access for development, testing, or production use cases. Since Ethereum is a protocol, there can be multiple independent networks that conform to the protocol without interacting with each other. Your Ethereum account will work across the different networks, but your account balance and transaction history won't carry over from the main Ethereum network. For testing purposes, it's useful to know which networks are available and how to get testnet ETH to play around with. In general, for security considerations, it's not recommended to reuse mainnet accounts on testnets or vice versa. Prerequisites. You should understand the basics of Ethereum before reading up on the different networks, as the test networks will give you a cheap, safe version of Ethereum to play around with. Public networks. Public networks are accessible to anyone in the world with an internet connection. Anyone can read or create transactions on a public blockchain and validate the transactions being executed. The consensus among peers decides on the inclusion of transactions and the state of the network. Ethereum mainnet. Mainnet is the primary public Ethereum production blockchain, where actual value transactions occur on the distributed ledger. Ethereum testnets. In addition to mainnet, there are public testnets. These are networks used by protocol developers or smart contract developers to test both protocol upgrades as well as potential smart contracts in a production like in Layer 2 testnets. Layer 2, L2, is a collective term to private networks. An Ethereum network is a private network if its nodes are not connected to a public network, i.e. mainnet or a testnet. In this context, private only means reserved or isolated, rather than protected or secure. Development networks. To develop an Ethereum application, you'll want to run it on a private network to see how it works before deploying it. Similar to how you create a local server on your computer for web development, you can create a local blockchain instance to test your dApp. This allows for much faster iteration than a public testnet. There are projects and tools dedicated to assist with this. Learn more about development networks. Consortium networks. The consensus process is controlled by a predefined set of nodes that are trusted. An approximate introduction to how ZK snarks are possible, why ZK snarks should be hard. Let us take the example that we started with. We have a number, we can encode cow followed by the secret input as an integer. We take the SHA-256 hash of that number. Then we do that again another 99,999,999 times. We get the output, and we check what its starting digits are. This is a huge computation. A succinct proof is one where both the size of the proof and the time required to verify it grow much more slowly than the computation to be verified. If we want a succinct proof, we cannot require the verifier to do some work per round of hashing, because then the verification time would be proportional to the computation. Instead, the verifier must somehow check the whole computation without peeking into each individual piece of the computation. One natural technique is random sampling. How about we just have the verifier peek into the computation in 500 different places, check that those parts are correct. And if all 500 checks pass, then assume that the rest of the computation must with high probability be fine, too. Such a procedure could even be turned into a non-interactive proof using the Fiat-Shamir heuristic. The prover computes a Merkle root of the computation, uses the Merkle root to pseudo-randomly choose 500 indices, and provides the 500 corresponding Merkle branches of the data. The key idea is that the prover does not know which branches they will need to reveal until they have already committed to the data. If a malicious prover tries to fudge the data after learning which indices are going to be checked, that would change the Merkle root, which would result in a new set of random indices, which would require fudging the data again, trapping the malicious prover in an endless cycle. But unfortunately, there is a fatal flaw in naively applying random sampling to spot check a computation in this way. Computation is inherently fragile. If a malicious prover flips one bit somewhere in the middle of a computation, they can make it give a completely different result, and a random sampling verifier would almost never find out. It only takes one deliberately inserted error, that a random check would almost never catch, to make a computation give a completely incorrect result. If tasked with the problem of coming up with a zk-snark protocol, many people would make their way to this point and then get stuck and give up. How can a verifier possibly check every single piece of the computation, without looking at each piece of the computation individually? But it turns out that there is a clever solution. Polynomials. Polynomials are a special class of algebraic expressions of the form x plus 5, x4, i.e. they are a sum of any finite number of terms of the form cxk. There are many things that are fascinating about polynomials, but here we are going to zoom in on a particular one. Polynomials are a single mathematical object that can contain an unbounded amount of information. Think of them as a list of integers, and this is obvious. The fourth example above contained 816 digits of tau, and one can easily imagine a polynomial that contains far more. Furthermore, a single equation between polynomials can represent an unbounded number of equations between numbers. For example, consider the equation a, x, plus b, x, equals c, x. If this equation is true, then it's also true that, and so on for every possible coordinate. You can even construct polynomials to deliberately represent sets of numbers so you can check many equations all at once. For example, suppose that you wanted to check. You can use a procedure called Lagrange interpolation to construct polynomials a, x, that give 12, 10, 15, 15 as outputs at some specific set of coordinates, e.g. 0, 1, 2, 3, b, x, the outputs, 1, 8, 8, 13, on those same coordinates, and so forth. In fact, here are the polynomials. A, x, equals 2x3 plus 192x2 192x plus 12. B, x, equals 2x3 192x2 plus 292x plus 1. C, x, equals 5x plus 13. Checking the equation a, x, plus b, x, equals c, x, with these polynomials checks all four above equations at the same time. Comparing a polynomial to itself. You can even check relationships between a large number of adjacent evaluations of the same polynomial using a simple polynomial equation. This is slightly more advanced. Suppose that you want to check that, for a given polynomial f, x plus 2, equals x plus 1, within the integer range 0, 1, 98, so if you also check 0, equals 1, equals 1, then 100, would be the 100th Fibonacci number. As polynomials, x plus 2, x plus 1, x, would not be exactly 0, as it could give arbitrary answers outside the range x equals 0, 1, 98. But we can do something clever. In general, there is a rule that if a polynomial p is 0 across some set s equals x1, x2, xn, then it can be expressed as p, x, equals z, x, h, x, where z, x, equals xx1, xx2, xxn, and h, x, is also a polynomial. In other words, any polynomial that equals 0 across some set is a polynomial, multiple of the simplest, lowest degree, polynomial that equals 0 across that same set. Why is this the case? It is a nice corollary of polynomial long division, the factor theorem. We know that, when dividing p, x, by z, x, we will get a quotient q, x, and a remainder r, x, which satisfy p, x, equals z, x, q, x, plus r, x, where the degree of the remainder r, x, is strictly less than that of z, x. Since we know that p is 0 on all of s, it means that r has to be 0 on all of s as well. So we can simply compute r, x, via polynomial interpolation, since it's a polynomial of degree at most n1 and we know n values, the zeros at s. Interpolating a polynomial with all zeros gives the zero polynomial, thus r, x, equals 0 and h, x, equals q, x. Going back to our example, if we have a polynomial f that encodes Fibonacci numbers, so x plus 2, equals x plus 1, across x equals 0, 1, 98. Then I can convince you that f actually satisfies this condition by proving that the polynomial p, x, equals x plus 2, x plus 1, x, is 0 over that range, by giving you the quotient h, x, equals x plus 2, x plus 1, x, z, x, where z, x, equals x0, x1, x98. You can calculate z, x, yourself. Ideally you would have it pre-computed, check the equation, and if the check passes then x, satisfies the condition. Now, step back, and notice what we did here. We converted a 100-step long computation, computing the 100th Fibonacci number, into a single equation with polynomials. Of course, proving the nth Fibonacci number is not an especially useful task, especially since Fibonacci numbers have a closed form. But you can use exactly the same basic technique, just with some extra polynomials and some more complicated equations, to encode arbitrary computations with an arbitrarily large number of steps. Now, if only there was a way to verify equations with polynomials that's much faster than checking each coefficient. Polynomial commitments. And once again, it turns out that there is an answer: polynomial commitments. A polynomial commitment is best viewed as a special way to hash a polynomial, where the hash has the additional property that you can check equations between polynomials by checking equations between their hashes. Different polynomial commitment schemes have different properties in terms of exactly what kinds of equations you can check. Here are some common examples of things you can do with various polynomial commitment schemes. We use com p to mean the commitment to the polynomial p. Add them, given com p, com q, and com r. Check if p plus q equals r. Multiply them, given com p, com q, and com r. Check if pq equals r. Evaluate at a point, given com p, w, z, and a supplemental proof, or witness, q, verify that p, w, equals z. It's worth noting that these primitives can be constructed from each other. If you can add and multiply, then you can evaluate. To prove that p, w, equals z, you can construct q, x, equals p, x, z x w, and the verifier can check if q, x, x w, plus z equals p, x. This works because if such a polynomial q, x, exists, then p, x, z equals q, x, x w, which means that p, x, z equals 0 at w, as x w equals 0 at w, and so p, x, equals z at w. And if you can evaluate, you can do all kinds of checks. This is because there is a mathematical theorem that says, approximately, that if some equation involving some polynomials holds true at a randomly selected coordinate, then it almost certainly holds true for the polynomials as a whole. So if all we have is a mechanism to prove evaluations, we can check e.g. our equation p, x plus 2, p, x plus 1, p, x, equals z, x, h, x, using an interactive game. As I alluded to earlier, we can make this non-interactive using the Fiat-Shamir heuristic. The prover can compute R themselves by setting R equals hash, com, p, com, h, where hash is any cryptographic hash function. It does not need any special properties. The prover cannot cheat by picking p and h that fit at that particular R but not elsewhere, because they do not know R at the time that they are picking p and h. A quick recap so far. ZK snarks are hard because the verifier needs to somehow check millions of steps in a computation, without doing a piece of work to check each individual step directly, as that would take too long. We get around this by encoding the computation into polynomials. A single polynomial can contain an unboundedly large amount of information, and a single polynomial expression, e.g. A single polynomial can contain an unboundedly large amount of information, and a single polynomial expression, e.g. p, x plus 2, p, x plus 1, p, x, equals z, x, h, x, can stand in for an unboundedly large number of equations between numbers. If you can verify the equation with polynomials, you are implicitly verifying all of the number equations. Replace x with any actual x coordinate, simultaneously. We use a special type of hash of a polynomial, called a polynomial commitment, to allow us to actually verify the equation between polynomials in a very short amount of time, even if the underlying polynomials are very large. So, how do these fancy polynomial hashes work? There are three major schemes that are widely used at the moment: bullet proofs, Kate, and Friday. Here is a description of Kate commitments by Dankradfeist, https://dankradfeist.de/ethereum/2020/06/16/Kate-polynomial-commitments.html. Here is a description of bullet proofs by the Curve 25519 team, https://doc-internal.dlk.rs/bulletproofs/notes/innerproductproof/index.html, and here is an explanation in pictures by myself. https://twitter.com/vitalikbutarin/status/1371844878968176647. Here is a description of Friday by myself, https://vitalikca/general/2017/11/22/starkspart2.html. Whoa, take it easy. Try to explain one of them simply, without shipping me off to even more scary links. To be honest, they're not that simple. There's a reason why all this math did not really take off until 2015 or so. Please? In my opinion, the easiest one to understand fully is Friday. Kate is easier if you are willing to accept elliptic curve pairings as a black box, but pairings are really complicated, so altogether I find Friday simpler. Here is how a simplified version of Friday works. The real protocol has many tricks and optimizations that are missing here for simplicity. Suppose that you have a polynomial p with degree. The commitment to p is a Merkle root of a set of evaluations to p at some set of preselected coordinates, e.g. 0, 1, 8 and 1, though this is not the most efficient choice. Now, we need to add something extra to prove that this set of evaluations actually is a degree. Let Q be the polynomial only containing the even coefficients of P, and R be the polynomial only containing the odd coefficients of P. So if P, x, equals x4 plus 4x3 plus 6x2 plus 4x plus 1, then Q, x, equals x2 plus 6x plus 1 and R, x, equals 4x plus 4. Note that the degrees of the coefficients get collapsed down to the range 0 and 2. Notice that P, x, equals Q, x2, plus xr, x2. If this isn't immediately obvious to you, stop and think and look at the example above until it is. We ask the prover to provide Merkle roots for Q, x, and R, x. We then generate a random number R and ask the prover to provide a random linear combination S, x, equals Q, x, plus R, x. We pseudo-randomly sample a large set of indices, using the already provided Merkle roots as the seed for the randomness as before, and ask the prover to provide the Merkle branches for P, Q, R, and S at these indices. At each of these provided coordinates, we check that P, x, actually does equal Q, x2, plus xr, x2. S, x, actually does equal Q, x, plus RR, x. If we do enough checks, then we can be convinced that the expected values of S, x, are different from the provided values in at most, say, 1% of cases. Notice that Q and R both have degree. Because S is a linear combination of Q and R, S also has degree. And this works in reverse, if we can prove S has degree. Then the fact that it's a randomly chosen combination prevents the prover from choosing malicious Q and R with hidden high degree coefficients that cancel out, so Q and R must both be degree. And because P, x, equals Q, x2, plus xr, x2, we know that P must have degree. From here, we simply repeat the game with S, progressively reducing the polynomial we care about to a lower and lower degree, until it's at a sufficiently low degree that we can check it directly. As in the previous examples, Bob here is an abstraction, useful for cryptographers to mentally reason about the protocol. In reality, Alice is generating the entire proof herself, and to prevent her from cheating we use fiat shamir. We choose each randomly sample's coordinate or R value based on the hash of the data generated in the proof up until that point. A full Friday commitment to P, in this simplified protocol, would consist of the Merkle root of evaluations of P, the Merkle roots of evaluations of Q, R, S1, the randomly selected branches of P, Q, R, S1 to check S1 is correctly reduced from P, the Merkle roots and randomly selected branches just as in steps 2 and 3, for successively lower degree reductions S2 reduced from S1, S3 reduced from S2, all the way down to a low degree SK. This gets repeated log 2, n, times in total. The full Merkle tree of the evaluations of SK, so we can check it directly. Each step in the process can introduce a bit of error, but if you add enough checks, then the total error will be low enough that you can prove that P, x, equals a degree. And this is sufficient for our use cases. If you want to cheat in a z-case narc, you would need to make a polynomial commitment for a fractional expression, e.g. to prove the false claim that x2 plus 2x plus 3 evaluated at 4 equals 5, you would need to provide a polynomial commitment for x2 plus 2x plus 3 5x4 equals x plus 6 plus 22x4. The set of evaluations for such a fractional expression would differ from the evaluations for any real degree. Also, you can check carefully that the total number and size of the objects in the Friday commitment is logarithmic in the degree, so for large polynomials, the commitment really is much smaller than the polynomial itself. To check equations between different polynomial commitments of this type, e.g. check A, x, plus B, x, equals C, x, given Friday commitments to A, B and C, simply randomly select many indices, ask the prover for Merkle branches at each of those indices for each polynomial, and verify that the equation actually holds true at each of those positions. The above description is a highly inefficient protocol. There is a whole host of algebraic tricks that can increase its efficiency by a factor of something like 100. And you need these tricks if you want a protocol that is actually viable for, say, use inside a blockchain transaction. In particular, for example, Q and R are not actually necessary, because if you choose your evaluation points very cleverly, you can reconstruct the evaluations of Q and R that you need directly from evaluations of P. But the above description should be enough to convince you that a polynomial commitment is fundamentally possible. Finite fields. In the descriptions above, there was a hidden assumption that each individual evaluation of a polynomial was small. But when we are dealing with polynomials that are big, this is clearly not true. If we take our example from above, 628x271 plus 318x270 plus 530x269 plus 69x plus 381, that encodes 816 digits of tau, and evaluate it at x equals 1000, you get an 816-digit number containing all of those digits of tau. And so there is one more thing that we need to add. In a real implementation, all of the arithmetic that we are doing here would not be done using regular arithmetic over real numbers. Instead, it would be done using modular arithmetic. We redefine all of our arithmetic operations as follows. We pick some prime modulus p. The percent operator means, take the remainder of 15% 7 equals 1, 53% 10 equals 3, etc. Note that the answer is always non-negative, so for example 1% 10 equals 9. We redefine x plus y, percent p. xy, percent p. xy, percent p. xy, percent p. x/y, xyp2, percent p. The above rules are all self-consistent. For example, if p equals 7, then 5 plus 3 equals 1, as 8% 7 equals 1. 1 3 equals 5, as 2% 7 equals 5. 2 5 equals 3. 3/5 equals 2, as 3 5 5% 7 equals 93 75% 7 equals 2. More complex identities such as the distributive law also hold. 2 plus 4, 3 and 2 3 plus 4 3 both evaluate to 4. Even formulas like a 2b2 equals a b, a plus b, are still true in this new kind of arithmetic. Division is the hardest part. We can't use regular division because we want the values to always remain integers, and regular division often gives non-integer results, as in the case of 3/5. We get around this problem using Fermat's little theorem, which states that for any non-zero x, This implies that xp2 gives a number which, if multiplied by x one more time, gives 1, and so we can say that xp2, which is an integer, equals 1x. A somewhat more complicated but faster way to evaluate this modular division operator is the extended Euclidean algorithm, implemented in Python here. Because of how the numbers wrap around, modular arithmetic is sometimes called clock math. With modular math we've created an entirely new system of arithmetic, and it's self-consistent in all the same ways traditional arithmetic is self-consistent. Hence, we can talk about all of the same kinds of structures over this field, including polynomials, that we talk about in regular math. Cryptographers love working in modular math, or, more generally, finite fields, because there is a bound on the size of a number that can arise as a result of any modular math calculation. No matter what you do, the values will not escape the set 0, 1, 2, p1. Even evaluating a degree 1-million polynomial in a finite field will never give an answer outside that set. What's a slightly more useful example of a computation being converted into a set of polynomial equations? Let's say we want to prove that, for some polynomial p, 0 less than or equal to p, n. This is a common use case in blockchain transactions, where you want to prove that a transaction leaves a balance non-negative without revealing what that balance is. We can construct a proof for this with the following polynomial equations, assuming for simplicity n equals 64. P, 0, equals 0. P, x plus 1, equals p, x, 2 plus r, x. The latter two statements can be restated as pure polynomial equations as follows. In this context z, x, equals x0, x1, x63. P, x plus 1, p, x, 2r, x, equals z. The idea is that successive evaluations of p, I, build up the number bit by bit. If p, 4, equals 13, then the sequence of evaluations going up to that point would be 0, 1, 3, 6, 13. In binary, 1 is 1, 3 is 11, 6 is 110, 13 is 1101. Notice how p, x plus 1, equals p, x, 2 plus r, x, keeps adding 1 bit to the end as long as r, x, is 0 or 1. Any number within the range 0 less than or equal to x. Privacy. But there is a problem. How do we know that the commitments to p, x, and r, x, don't leak information that allows us to uncover the exact value of p, 64, which we are trying to keep hidden? There is some good news. These proofs are small proofs that can make statements about a large amount of data and computation. So in general, the proof will very often simply not be big enough to leak more than a little bit of information. But can we go from only a little bit to 0? Fortunately, we can. Here, one fairly general trick is to add some fudge factors into the polynomials. When we choose p, add a small multiple of z, x, into the polynomial, that is, set p, x, equals p, x, plus z, x, e, x, for some random e, x. This does not affect the correctness of the statement. In fact, p evaluates to the same values as p on the coordinates that the computation is happening in, so it's still a valid transcript. But it can add enough extra noise into the commitments to make any remaining information unrecoverable. Additionally, in the case of Friday, it's important to not sample random points that are within the domain that computation is happening in this case 0, 64. Can we have one more recap, please? The three most prominent types of polynomial commitments are Friday, Kate, and bullet proofs. Kate is the simplest conceptually but depends on the really complicated black box of elliptic curve pairings. Friday is cool because it relies only on hashes. It works by successively reducing a polynomial to a lower and lower degree polynomial and doing random sample checks with Merkle branches to prove equivalence at each step. To prevent the size of individual numbers from blowing up, instead of doing arithmetic in polynomials over the integers, we do everything over a finite field, usually integers modulo some prime p. Polynomial commitments lend themselves naturally to privacy preservation because the proof is already much smaller than the polynomial, so a polynomial commitment can't reveal more than a little bit of the information in the polynomial anyway. But we can add some randomness to the polynomials we're committing to reduce the information revealed from a little bit to 0. What research questions are still being worked on? Optimizing Friday. There are already quite a few optimizations involving carefully selected evaluation domains, Deep Friday, and a whole host of other tricks to make Friday more efficient. Starkware and others are working on this. Better ways to encode computation into polynomials, figuring out the most efficient way to encode complicated computations involving hash functions, memory access, and other features into polynomial equations is still a challenge. There has been great progress on this, e.g. C++, but we still need more, especially if we want to encode general-purpose virtual machine execution into polynomials. Incrementally verifiable computation. It would be nice to be able to efficiently keep extending a proof while a computation continues. This is valuable in the single prover case, but also in the multi-prover case, particularly a blockchain where a different participant creates each block. See Halo for some recent work on this. Gasper. Last edit at WAC. Gasper is a combination of Casper the friendly finality gadget, Casper FFG, and the LMD Ghost fork choice algorithm. Together these components form the consensus mechanism securing proof-of-stake Ethereum. Casper is the mechanism that upgrades certain blocks to finalized so that new entrants into the network can be confident that they are syncing the canonical chain. The fork choice algorithm uses accumulated votes to ensure that nodes can easily select the correct one when forks arise in the blockchain. Note that the original definition of Casper FFG was updated slightly for inclusion in Gasper. On this page we consider the updated version. Prerequisites. To understand this material it is necessary to read the introductory page on proof of stake. The role of Gasper. Gasper sits on top of a proof of stake blockchain where nodes provide Ether as a security deposit that can be destroyed if they are lazy or dishonest in proposing or validating blocks. Gasper is the mechanism defining how validators get rewarded and punished, decide which blocks to accept and reject, and which fork of the blockchain to build on. What is finality? Finality is a property of certain blocks that means they cannot be reverted unless there has been a critical consensus failure and an attacker has destroyed at least 1/3 of the total staked Ether. Finalized blocks can be thought of as information the blockchain is certain about. A block must pass through a two-step upgrade procedure for a block to be finalized. 2/3 of the total staked Ether must have voted in favor of that block's inclusion in the canonical chain. This condition upgrades the block to justified. Justified blocks are unlikely to be reverted, but they can be under certain conditions. When another block is justified on top of a justified block, it is upgraded to finalized. Finalizing a block is a commitment to include the block in the canonical chain. It cannot be reverted unless an attacker destroys millions of Ether, billions of $USD. These block upgrades do not happen in every slot. Instead, only epoch boundary blocks can be justified and finalized. These blocks are known as checkpoints. Upgrading considers pairs of checkpoints. A supermajority link must exist between two successive checkpoints, i.e. 2/3 of the total staked Ether voting that checkpoint B is the correct descendant of checkpoint A, to upgrade the less recent checkpoint to finalized and the more recent block to justified. Because finality requires a 2/3 agreement that a block is canonical, an attacker cannot possibly create an alternative finalized chain without owning or manipulating 2/3 of the total staked Ether. Destroying at least 1/3 of the total staked Ether. The first condition arises because 2/3 of the staked Ether is required to finalize a chain. The second condition arises because if 2/3 of the total stake has voted in favor of both forks, then 1/3 must have voted on both. Double voting is a slashing condition that would be maximally punished, and 1/3 of the total stake would be destroyed. As of May 2022, this requires an attacker to burn around $10 billion worth of Ether. The algorithm that justifies and finalizes blocks in Gasper is a slightly modified form of Casper, the friendly finality gadget, Casper FFG. Incentives and slashing. Validators get rewarded for honestly proposing and validating blocks. Ether is rewarded and added to their stake. On the other hand, validators that are absent and fail to act when called upon miss out on these rewards and sometimes lose a small portion of their existing stake. However, the penalties for being offline are small and, in most cases, amount to opportunity costs of missing rewards. However, some validator actions are very difficult to do accidentally and signify some malicious intent, such as proposing multiple blocks for the same slot, attesting to multiple blocks for the same slot, or contradicting previous checkpoint votes. These are slashable behaviors that are penalized more harshly. Slashing results in some portion of the validator's stake being destroyed and the validator being removed from the network of validators. This process takes 36 days. On day 1, there is an initial penalty of up to 0.5 ETH. Then the slashed validator's Ether slowly drains away across the exit period, but on day 18, they receive a correlation penalty, which is larger when more validators are slashed around the same time. The maximum penalty is the entire stake. These rewards and penalties are designed to incentivize honest validators and disincentivize attacks on the network. Inactivity leak. As well as security, Gasper also provides plausible liveness. This is the condition that as long as 2/3 of the total staked Ether is voting honestly and following the protocol, the chain will be able to finalize irrespective of any This is the condition that as long as 2/3 of the total staked Ether is voting honestly and following the protocol, the chain will be able to finalize irrespective of any other activity, such as attacks, latency issues, or slashings. Put another way, 1/3 of the total staked Ether must be somehow compromised to prevent the chain from finalizing. In Gasper, there is an additional line of defense against a liveness failure, known as the inactivity leak. This mechanism activates when the chain has failed to finalize for more than 4 epochs. The validators that are not actively attesting to the majority chain have their stake gradually drained away until the majority regains 2/3 of the total stake, ensuring that liveness failures are only temporary. Fork choice. The original definition of Casper FFG included a fork choice algorithm that imposed the rule, follow the chain containing the justified checkpoint that has the greatest height, where height is defined as the greatest distance from the genesis block. In Gasper, the original fork choice rule is deprecated in favor of a more sophisticated algorithm called LMD Ghost. It is important to realize that under normal conditions, a fork choice rule is unnecessary. There is a single block proposer for every slot, and honest validators attest to it. It is only in cases of large network asynchronicity or when a dishonest block proposer has equivocated that a fork choice algorithm is required. However, when those cases do arise, the fork choice algorithm is a critical defense that secures the correct chain. LMD Ghost stands for latest message driven greedy heaviest observed subtree. This is a jargon-heavy way to define an algorithm that selects the fork with the greatest accumulated weight of attestations as the canonical one, greedy heaviest subtree, and that if multiple messages are received from a validator, only the latest one is considered latest message driven. Before adding the heaviest block to its canonical chain, every validator assesses each block using this rule. Further reading. Gasper, weak subjectivity. Subjectivity in blockchains refers to reliance upon social information to agree on the current state. There may be multiple valid forks that are chosen from according to information gathered from other peers on the network. The converse is objectivity, which refers to chains where there is only one possible valid chain that all nodes will necessarily agree upon by applying their coded rules. There is also a third state, known as weak subjectivity. This refers to a chain that can progress objectively after some initial seed of information is retrieved socially. Prerequisites. To understand this page, it is necessary to first understand the fundamental. What problems does weak subjectivity solve? Subjectivity is inherent to proof-of-stake blockchains because selecting the correct chain from multiple forks is done by counting historical votes. This exposes the blockchain to several attack vectors, including long-range attacks whereby nodes that participated very early in the chain maintain an alternative fork that they release much later to their own advantage. Alternatively, if 33% of validators withdraw their stake but continue to attest and produce blocks, they might generate an alternative fork that conflicts with the canonical chain. New nodes or nodes that have been offline for a long time might not be aware that these attacking validators have withdrawn their funds, so attackers could trick them into following an incorrect chain. Ethereum can solve these attack vectors by imposing constraints that diminish the subjective aspects of the mechanism and therefore trust assumptions to the bare minimum. Weak subjectivity checkpoints. Weak subjectivity is implemented in proof-of-stake Ethereum by using weak subjectivity checkpoints. These are state roots that all nodes on the network agree belong in the canonical chain. They serve the same, universal truth, purpose to genesis blocks, except that they do not sit at the genesis position in the blockchain. The fork choice algorithm trusts that the blockchain state defined in that checkpoint is correct and that it independently and objectively verifies the chain from that point onwards. The checkpoints act as revert limits, because blocks located before weak subjectivity checkpoints cannot be changed. This undermines long-range attacks simply by defining long-range forks to be invalid as part of the mechanism design. Ensuring that the weak subjectivity checkpoints are separated by a smaller distance than the validator withdrawal period ensures that a validator that forks the chain is slashed at least some threshold amount before they can withdraw their stake and that new entrants cannot be tricked onto incorrect forks by validators whose stake has been withdrawn. Difference between weak subjectivity checkpoints and finalized blocks. Finalized blocks and weak subjectivity checkpoints are treated differently by Ethereum nodes. If a node becomes aware of two competing finalized blocks, then it is torn between the two. It has no way to identify automatically which is the canonical fork. This is symptomatic of a consensus failure. In contrast, a node simply rejects any block that conflicts with its weak subjectivity checkpoint. From the node's perspective, the weak subjectivity checkpoint represents an absolute truth that cannot be undermined by new knowledge from its peers. How weak is weak? The subjective aspect of Ethereum's proof-of-stake is the requirement for a recent state, weak subjectivity checkpoint, from a trusted source to sync from. The risk of getting a bad weak subjectivity checkpoint is very low because they can be checked against several independent public sources such as block explorers or multiple nodes. However, there is always some degree of trust required to run any software application, for example, trusting that the software developers have produced honest software. A weak subjectivity checkpoint may even come as part of the client software. Arguably, an attacker can corrupt the checkpoint in the software and can just as easily corrupt the software itself. There is no real crypto-economic route around this problem, but the impact of untrustworthy developers is minimized in Ethereum by having multiple independent client teams, each building equivalent software in different languages, all with a vested interest in maintaining an honest chain. Block explorers may also provide weak subjectivity checkpoints or a way to cross-reference checkpoints obtained from elsewhere against an additional source. Finally, checkpoints can be requested from other nodes. Perhaps another Ethereum user that runs a full node can provide a checkpoint that validators can then verify against data from a block explorer. Overall, trusting the provider of a weak subjectivity checkpoint can be considered as problematic as trusting the client developers. The overall trust required is low. It is important to note that these considerations only become important in the very unlikely event that a majority of validators conspire to produce an alternate fork of the blockchain. Under any other circumstances, there is only one Ethereum chain to choose from. Further reading. Weak subjectivity in Eth2. Attestations. A validator is expected to create, sign and broadcast an attestation during every epoch. This page outlines what these attestations look like and how they are processed and communicated between consensus clients. What is an attestation? Every epoch, 6.4 minutes, a validator proposes an attestation to the network. The attestation is for a specific slot in the epoch. The purpose of the attestation is to vote in favor of the validator's view of the chain, in particular the most recent justified block and the first block in the current epoch, known as source and target checkpoints. This information is combined for all participating validators, enabling the network to reach consensus about the state of the blockchain. The attestation contains the following components. Aggregation bits, a bit list of validators where the position maps to the validator index in their committee. The value, 0/1, indicates whether the validator signed the data, i.e. whether they are active and agree with the block proposer. Data, details relating to the attestation, as defined below. Signature, a BLS signature that aggregates the signatures of individual validators. The first task for an attesting validator is to build the data. The data contains the following information. Slot, the slot number that the attestation refers to. Index, a number that identifies which committee the validator belongs to in a given slot. Beacon block root hash of the block the validator sees at the head of the chain, the result of applying the fork choice algorithm. Source, part of the finality vote indicating what the validator see as the most recent justified block. Target, part of the finality vote indicating what the validator see as the first block in the current epoch. Once the data is built, the validator can flip the bit in aggregation bits corresponding to their own validator index from 0 to 1 to show that they participated. Finally, the validator signs the attestation and broadcasts it to the network. Aggregated attestation. There is a substantial overhead associated with passing this data around the network for every validator. Therefore, the attestations from individual validators are aggregated within subnets before being broadcast more widely. This includes aggregating signatures together so that an attestation that gets broadcast includes the consensus data and a single signature formed by combining the signatures of all the validators that agree with that data. This can be checked using aggregation bits because this provides the index of each validator and their committee, whose ID is provided in data, which can be used to query individual signatures. In each epoch, a validator in each subnet is selected to be the aggregator. The aggregator collects all the attestations it hears about over the gossip network that have equivalent data to its own. The sender of each matching attestation is recorded in the aggregation bits. The aggregator then broadcasts the attestation aggregate to the wider network. When a validator is selected to be a block proposer, they package aggregate attestations from the subnets up to the latest slot in the new block. Attestation inclusion lifecycle. Generation. Propagation. Aggregation. Propagation. Inclusion. The attestation life cycle is outlined in the schematic below. Rewards. Rewards. Validators are rewarded for submitting attestations. The attestation reward is dependent on two variables, the base reward and the inclusion delay. The best case for the inclusion delay is to be equal to 1. Attestation reward equals 7/8 x base reward x, 1/inclusion delay. Base reward. The base reward is calculated according to the number of attesting validators and their effective staked ether balances. Base reward equals inclusion delay. At the time when the validators voted on the head of the chain, block n plus 1 was not proposed yet. Therefore attestations naturally get included one block later, so all attestations who voted on block n being the chain head got included in block n plus 1 and the inclusion delay is 1. If the inclusion delay doubles to 2 slots, the attestation reward halves, because to calculate the attestation reward the base reward is multiplied by the reciprocal of the inclusion delay. Attestation scenarios. Missing voting validator. Validators have a maximum of 1 epoch to submit their attestation. If the attestation was missed in epoch 0, they can submit it with an inclusion delay in epoch 1. Missing aggregator. There are 16 aggregators per epoch in total. In addition, random validators subscribe to 2 subnets for 256 epochs and serve as a backup in case aggregators are missing. Missing block proposer. Note that in some cases a lucky aggregator may also become the block proposer. If the attestation was not included because the block proposer has gone missing, the next block proposer would pick the aggregated attestation up and include it into the next block. However, the inclusion delay will increase by 1. Further reading. Attestations in vital proof of stake rewards and penalties. Ethereum is secured using its native cryptocurrency, Ether, ETH. Node operators that wish to participate in validating blocks and identifying the head of the chain deposit Ether into a smart contract on Ethereum. They are then paid in Ether to run validator software that checks the validity of new blocks received over the peer-to-peer network and apply the fork choice algorithm to identify the head of the chain. There are 2 primary roles for a validator: 1. Checking new blocks and attesting to them if they are valid; 2. Proposing new blocks when selected at random from the total validator pool. If the validator fails to do either of these tasks when asked, they miss out on an Ether payout. Validators are also sometimes tasked with signature aggregation and participating in sync committees. There are also some actions that are very difficult to do accidentally and signify some malicious intent, such as proposing multiple blocks for the same slot or attesting to multiple blocks for the same slot. These are slashable behaviors that result in the validator having some amount of Ether, up to 1 ETH, burned before the validator is removed from the network, which takes 36 days. The slashed validator's Ether slowly drains away across the exit period, but on day 18 they receive a correlation penalty, which is larger when more validators are slashed around the same time. The beacon chain's incentive structure therefore pays for honesty and punishes bad actors. All rewards and penalties are applied once per epoch. Read on for more details. Rewards and penalties. Rewards. Validators receive rewards when they make votes that are consistent with the majority of other validators, when they propose blocks, and when they participate in sync committees. The value of the rewards in each epoch are calculated from a base reward. This is the base unit that other rewards are calculated from. The base reward represents the average reward received by a validator under optimal conditions per epoch. This is calculated from the validator's effective balance and the total number of active validators as follows. 1 base reward equals effect, where base reward factor is 64, base rewards per epoch is 4 and sum, active balance, is the total staked Ether across all active validators. This means the base reward is proportional to the validator's effective balance and inversely proportional to the number of validators on the network. The more validators, the greater the overall issuance, as SQRT, N, but the smaller the base reward per validator, as 1/SQRT, N. These factors influence the APR for a staking node. Read the rationale for this in Vitalix notes. The total reward is then calculated as the sum of 5 components that each have a weighting that determines how much each component adds to the total reward. The components are 11. Source vote. The validator has made a timely vote for the correct source checkpoint 22. Target vote. The validator has made a timely vote for the correct target checkpoint 33. Head vote. The validator has made a timely vote for the correct head block 44. Sync committee reward. The validator has participated in a sync committee 55. Proposer reward. The validator has proposed a block in the correct slot 6. The weightings for each component are as follows. 1 time source weight UIN 64, 14, 2 time target weight UIN 64, 26. These weights sum to 64. The reward is calculated as the sum of the applicable weights divided by 64. A validator that has made timely source, target, and head votes, proposed a block and participated in a sync committee could receive 64/64 base reward equals base reward. However, a validator is not usually a block proposer, so their maximum reward is 64 to 8/64 base reward equals 7/8 base reward. Validators that are neither block proposers nor in a sync committee can receive August 2nd, 64/64. An additional reward is added to incentivize rapid attestations. This is the inclusion delay reward. This has a value equal to the base reward multiplied by 1/delay, where delay is the number of slots separating the block proposal and attestation. For example, if the attestation is submitted within 1 slot of the block proposal, the attester receives base reward *1/1 equals base reward. If the attestation arrives in the next slot, block proposers receive 8/64 base reward for each valid attestation included in the block, so the actual value of the reward scales with the number of attesting validators. Block proposers can also increase their reward by including evidence of misbehavior by other validators in their proposed block. These rewards are the carrots that encourage validator honesty. A block proposer which includes slashing will be rewarded with the slashed validator's effective balance penalties. So far we have considered perfectly well-behaved validators, but what about validators that do not make timely head, source, and target votes or do so slowly? The penalties for missing the target and source votes are equal to the rewards the attester would have received had they submitted them. This means that instead of having the reward added to their balance, they have an equal value removed from their balance. There is no penalty for missing the head vote, i.e. head votes are only rewarded, never penalized. There is no penalty associated with the inclusion delay, the reward will simply not be added to the validator's balance. There is also no penalty for failing to propose a block. Read more about rewards and penalties in the consensus specs. Rewards and penalties were adjusted in the Bellatrix upgrade. Watch Danny Ryan and Vitalik discuss this in this PEEP and EIP video. Slashing. Slashing is a more severe action that results in the forceful removal of a validator from the network and an associated loss of their staked ether. There are 3 ways a validator can be slashed, all of which amount to the dishonest proposal or attestation of blocks. By proposing and signing 2 different blocks for the same slot. By attesting to a block that surrounds another one, effectively changing history. By double voting, by attesting to 2 candidates for the same block. If these actions are detected, the validator is slashed. This means that 1/32 of their staked ether, up to a maximum of 1 ether, is immediately burned, then a 36-day removal period begins. During this removal period the validator's stake gradually bleeds away. At the midpoint, day 18, an additional penalty is applied whose magnitude scales with the total staked ether of all slashed validators in the 36 days prior to slashing event. This means that when more validators are slashed, the magnitude of the slash increases. The maximum slash is the full effective balance of all slashed validators, i.e. if there are lots of validators being slashed they could lose their entire stake. On the other hand, a single, isolated slashing event only burns a small portion of the validator's stake. This midpoint penalty that scales with the number of slashed validators is called the correlation penalty. Inactivity leak. If the beacon chain has gone more than 4 epochs without finalizing, an emergency protocol called the inactivity leak is activated. The ultimate aim of the inactivity leak is to create the conditions required for the chain to recover finality. As explained above, finality requires a 2/3 majority of the total staked ether to agree on source and target checkpoints. If validators representing more than 1/3 of the total validators go offline or fail to submit correct attestations, then it is not possible for a 2/3 supermajority to finalize checkpoints. The inactivity leak lets the stake belonging to the inactive validators gradually bleed away until they control less than 1/3 of the total stake, allowing the remaining active validators finalize the chain. However large the pool of inactive validators, the remaining active validators will eventually control 2/3 of the stake. The loss of stake is a strong incentive for inactive validators to reactivate as soon as possible. An inactivity leak scenario was encountered on the Medalla testnet when the inactivity leak was activated and finality was eventually regained. The reward, penalty, and slashing design of the beacon chain encourages individual validators to behave correctly. However, from these design choices emerges a system that strongly incentivizes equal distribution of validators across multiple clients, and should strongly disincentivize single client dominance. Further reading. Upgrading Ethereum. Ethereum proof of stake attack and defense. Thieves and saboteurs are constantly seeking opportunities to attack Ethereum's client software. This page outlines the known attack vectors on Ethereum's consensus layer and outlines how those attacks can be defended. The information on this page is adapted from a longer form version. Prerequisites. Some basic knowledge of proof of stake is required. Also, it will be helpful to have a basic understanding of Ethereum's incentive layer and fork choice algorithm, LMD Ghost. What do attackers want? A common misconception is that a successful attacker can generate new ether, or drain ether from arbitrary accounts. Neither of these are possible because all transactions are executed by all the execution clients on the network. They must satisfy basic conditions of validity, e.g. transactions are signed by sender's private key, sender has sufficient balance, etc., or else they simply revert. There are 3 classes of outcome that an attacker might realistically target: reorgs, double finality, or finality delay. A reorg is a reshuffling of blocks into a new order, perhaps with some addition or subtraction of blocks in the canonical chain. A malicious reorg might ensure specific blocks are included or excluded, allowing double spending or value extraction by front-running and back-running transactions, MEV. Reorgs could also be used to prevent certain transactions from being included in the canonical chain, a form of censorship. The most extreme form of reorg is finality reversion, which removes or replaces blocks that have previously been finalized. This is only possible if more than 1/3 of the total staked ether is destroyed by the attacker. This guarantee is known as economic finality, more on this later. Double finality is the unlikely but severe condition where 2 forks are able to finalize simultaneously, creating a permanent schism in the chain. This is theoretically possible for an attacker willing to risk 34% of the total staked ether. The community would be forced to coordinate off-chain and come to an agreement about which chain to follow, which would require strength in the social layer. A finality delay attack prevents the network from reaching the necessary conditions finalizing sections of the chain. Without finality, it is hard to trust financial applications built on top of Ethereum. The aim of a finality delay attack is likely simply to disrupt Ethereum rather than to directly profit, unless the attacker has some strategic short position, S. An attack on the social layer might aim to undermine public trust in Ethereum, devalue Ether, reduce adoption, or to weaken the Ethereum community to make out-of-band coordination more difficult. Having established why an adversary might attack Ethereum, the following sections examine how they might go about it. Methods of attack. Layer 0 attacks. First of all, individuals that are not actively participating in Ethereum, by running client software, can attack by targeting the social layer, Layer 0. Layer 0 is the foundation upon which Ethereum is built, and as such it represents a potential surface for attacks with consequences that ripple through the rest of the stack. Some examples might include A misinformation campaign could erode the trust the community has in Ethereum's roadmap, teams of developers, apps, etc. This could then decrease the number of individuals willing to participate in securing the network, degrading both decentralization and crypto-economic security. Targeted attacks and/or intimidation directed at the developer community. This could lead to voluntary exit of developers and slow down Ethereum's progress. Overzealous regulation could also be considered to be an attack on Layer 0, since it could rapidly disincentivize participation and adoption. Infiltration of knowledgeable but malicious actors into the developer community whose aim is to slow down progress by bike-shedding discussions, delaying key decisions, creating spam, etc. Bribes made to key players in the Ethereum ecosystem to influence decision-making. What makes these attacks especially dangerous is that in many cases very little capital or technical know-how is required. A Layer 0 attack could be a multiplier on a crypto-economic attack. For example, if censorship or finality reversion were achieved by a malicious majority stakeholder, undermining the social layer might make it more difficult to coordinate a community response out of band. Defending against Layer 0 attacks is probably not straightforward, but some basic principles can be established. One is maintaining an overall high signal-to-noise ratio for public information about Ethereum, created and propagated by honest members of the community through blogs, Discord servers, annotated specs, books, podcasts, and YouTube. Here at Ethereum.org we try hard to maintain accurate information and translate it into as many languages as possible. Flooding a space with high-quality information and memes is an effective defense against misinformation. Another important fortification against social layer attacks is a clear mission statement and governance protocol. Ethereum has positioned itself as the decentralization and security champion among smart contract layer 1s, while also highly valuing scalability and sustainability. Whatever disagreements arise in the Ethereum community, these core principles are minimally compromised. Appraising a narrative against these core principles, and examining them through successive rounds of review in the EIP, Ethereum Improvement Proposal, process, might help the community to distinguish good from bad actors and limits the scope for malicious actors to influence the future direction of Ethereum. Finally, it is critical that the Ethereum community remains open and welcoming to all participants. A community with gatekeepers and exclusivity is one especially vulnerable to social attack because it is easy to build us and them narratives. Tribalism and toxic maximalism hurt the community and erode Layer 0 security. Ethereans with a vested interest in the security of the network should view their conduct online and in meet space as attacking the protocol. Anyone can run Ethereum's client software. To add a validator to a client, a user is required to stake 32 Ether into the deposit contract. A validator allows a user to actively participate in Ethereum's network security by proposing and attesting to new blocks. The validator now has a voice they can use to influence the future contents of the blockchain. They can do so honestly and grow their stash of Ether via rewards, or they can try to manipulate the process to their own advantage, risking their stake. One way to mount an attack is to accumulate a greater proportion of the total stake and then use it to outvote honest validators. The greater the proportion of the stake controlled by the attacker, the greater their voting power, especially at certain economic milestones that we will explore later. However, most attackers will not be able to accumulate sufficient Ether to attack in this way, so instead they have to use subtle techniques to manipulate the honest majority into acting a certain way. Fundamentally, all small-stake attacks are subtle variations on two types of validator misbehavior: underactivity, failing to attest/propose or doing so late, or overactivity, proposing/attesting too many times in a slot. In their most vanilla forms, these actions are easily handled by the fork choice algorithm and incentive layer, but there are clever ways to game the system to an attacker's advantage. Attacks using small amounts of ETH. Reorgs. Several papers have explained attacks on Ethereum that achieve reorgs or finality delay with only a small proportion of the total staked Ether. These attacks generally rely upon the attacker withholding some information from other validators and then releasing it in some nuanced way and/or at some opportune moment. They usually aim to displace some honest block, S, from the canonical chain. Nutter et al. 2020 showed how an attacking validator can create and attest to a block, B, for a particular slot n+1 but refrain from propagating it to other nodes on the network. Instead, they hold on to that attested block until the next slot n+2. An honest validator proposes a block, C, for slot n+2. Almost simultaneously, the attacker can release their withheld block, B, and their withheld attestations for it, and also attest to B being the head of the chain with their votes for slot n+2. Effectively denying the existence of honest block C. When honest block D is released, the fork choice algorithm sees D building on top of B being heavier than D building on C. The attacker has therefore managed to remove the honest block C in slot n+2 from the canonical chain using a 1 block X anti-reorg. An attacker with 34% of the stake has a very good chance of succeeding in this attack, as explained in this note. In theory, though, this attack could be attempted with smaller stakes. Nutter et al. 2020 described this attack working with a 30% stake, but it was later shown to be viable with 2% of the total stake and then again for a single validator using balancing techniques we will examine in the next section. A conceptual diagram of the one-block reorg attack described above, adapted from https://notes.ethereum.org/plgvdz-or-fgjk06bz3a #fork-choice-by-block-pair. A more sophisticated attack can split the honest validator set into discrete groups that have different views of the head of the chain. This is known as a balancing attack. The attacker waits for their chance to propose a block, and when it arrives they equivocate and propose two. They send one block to half of the honest validator set and the other block to the other half. The equivocation would be detected by the fork choice algorithm and the block proposer would be slashed and ejected from the network, but the two blocks would still exist and would have about half the validator set attesting to each fork. Meanwhile, the remaining malicious validators hold back their attestations. Then, by selectively releasing the attestations favoring one or other fork to just enough validators just as the fork choice algorithm executes, they tip the accumulated weight of attestations in favor of one or other fork. This can continue indefinitely, with the attacking validators maintaining an even split of validators across the two forks. Since neither fork can attract a 2/3 supermajority, the beacon chain would not finalize. Bouncing attacks are similar. Votes are again withheld by the attacking validators. Instead of releasing the votes to keep an even split between two forks, They use their votes at opportune moments to justify checkpoints that alternate between fork A and fork B. This flip-flopping of justification between two forks prevents there from being pairs of justified source and target checkpoints that can be finalized on either chain, halting finality. Both bouncing and balancing attacks rely upon the attacker having very fine control over message timing across the network, which is unlikely. Nevertheless, defenses are built into the protocol in the form of additional weighting given to prompt messages compared to slow ones. This is known as proposer weight boosting. To defend against bouncing attacks, the fork choice algorithm was updated so that the latest justified checkpoint can only switch to that of an alternative chain during the first one-third of the slots in each epoch. This condition prevents the attacker from saving up votes to deploy later. The fork choice algorithm simply stays loyal to the checkpoint it chose in the first one-third of the epoch, during which time most honest validators would have voted. Combined, these measures create a scenario in which an honest block proposer emits their block very rapidly after the start of the slot. Then there is a period of 1/3 of a slot, 4 seconds, where that new block might cause the fork choice algorithm to switch to another chain. After that same deadline, attestations that arrive from slow validators are downweighted compared to those that arrived earlier. This strongly favors prompt proposers and validators in determining the head of the chain and substantially reduces the likelihood of a successful balancing or bouncing attack. It is worth noting that proposer boosting alone only defends against cheap reorgs, i.e. those attempted by an attacker with a small stake. In fact, proposer boosting itself can be gamed by larger stakeholders. The authors of this post describe how an attacker with 7% of the stake can deploy their votes strategically to trick honest validators to build on their fork, re-urging out an honest block. This attack was devised assuming ideal latency conditions that are very unlikely. The odds are still very long for the attacker, and the greater stake also means more capital at risk and a stronger economic disincentive. A balancing attack specifically targeting the LMD rule was also proposed, which was suggested to be viable in spite of proposer boosting. An attacker sets up two competing chains by equivocating their block proposal and propagating each block to about half the network each, setting up an approximate balance between the forks. Then, the colluding validators equivocate their votes, timing it so that half the network receive their votes for fork A first and the other half receives their votes for fork B first. Since the LMD rule discards the second attestation and keeps only the first for each validator, half the network sees votes for A and none for B. The other half sees votes for B and none for A. The authors describe the LMD rule giving the adversary remarkable power to mount a balancing attack. This LMD attack vector was closed by updating the fork choice algorithm so that it discards equivocating validators from the fork choice consideration altogether. Equivocating validators also have their future influence discounted by the fork choice algorithm. This prevents the balancing attack outlined above while also maintaining resilience against avalanche attacks. Another class of attack, called avalanche attacks, was described in a March 2022 paper. To mount an avalanche attack, the attacker needs to control several consecutive block proposers. In each of the block proposal slots, the attacker withholds their block, collecting them up until the honest chain reaches an equal subtree weight with the withheld blocks. Then, the withheld blocks are released so that they equivocate maximally. The authors suggest that proposer boosting, the primary defense against balancing and bouncing attacks, does not protect against some variants of avalanche attack. However, the authors also only demonstrated the attack on a highly idealized version of Ethereum's fork choice algorithm. They used Ghost without LMD. The avalanche attack is mitigated by the LMD portion of the LMD Ghost fork choice algorithm. LMD means latest message driven and it refers to a table kept by each validator containing the latest message received from other validators. That field is only updated if the new message is from a later slot than the one already in the table for a particular validator. In practice, this means that in each slot, the first message received is the one that it accepted and any additional messages or equivocations to be ignored. Put another way, the consensus clients don't count equivocations, they use the first arriving message from each validator and equivocations are simply discarded, preventing avalanche attacks. There are several other potential future upgrades to the fork choice rule that could add to the security provided by Proposer Boost. One is view merge, where attesters freeze their view of the fork choice n seconds before the beginning of a slot and the proposer then helps to synchronize the view of the chain across the network. Another potential upgrade is single slot finality, which protects against attacks based on message timing by finalizing the chain after just one slot. Finality delay. The same paper that first described the low-cost single-block reorg attack also described a finality delay, aka liveness failure, attack that relies on the attacker being the block proposer for an epoch boundary block. This is critical because these epoch boundary blocks become the checkpoints that cast attacker controlling the validator proposing a given epoch boundary block. Long-range attacks. There is also a class of attack specific to proof-of-stake blockchains that involves a validator that participated in the genesis block maintaining a separate fork of the blockchain alongside the honest one, eventually convincing the honest validator set to switch over to it at some opportune time much later. This type of attack is not possible on Ethereum because of the finality gadget that ensures all validators agree on the state of the honest chain at regular intervals, checkpoints. This simple mechanism neutralizes long-range attackers because Ethereum clients simply will not reorg finalized blocks. New nodes joining the network do so by finding a trusted recent state hash, a weak subjectivity checkpoint, and using it as a pseudo-genesis block to build on top of. This creates a trust gateway for a new node entering the network before it can start to verify information for itself. Denial of service. Ethereum's POS mechanism picks a single validator from the total validator set to be a block proposer in each slot. This can be computed using a publicly known function and it is possible for an adversary to identify the next block proposer slightly in advance of their block proposal. Then, the attacker can spam the block proposer to prevent them swapping information with their peers. To the rest of the network, it would appear that the block proposer was offline and the slot would simply go empty. This could be a form of censorship against specific validators, preventing them from adding information to the blockchain. Implementing single secret leader elections, SSLE, or non-single secret leader elections will mitigate those risks because only the block proposer ever knows they have been selected and the selection is not knowable in advance. This is not yet implemented, but is an active area of research and development. All of this points to the fact that it is very difficult to successfully attack Ethereum with a small stake. The viable attacks that have been described here require an idealized fork choice algorithm, improbable network conditions, or the attack vectors have already been closed with relatively minor patches to the client software. This, of course, does not rule out the possibility of 0 days existing out in the wild, but it does demonstrate the extremely high bar of technical aptitude, consensus layer knowledge and luck required for a minority stake attacker to be effective. From an attacker's perspective, their best bet might be to accumulate as much ether as possible and to return armed with a greater proportion of the total stake. Attackers using equals 33% of the total stake. All of the attacks mentioned previously in this article become more likely to succeed when the attacker has more staked ether to vote with, and more validators that might be chosen to propose blocks in each slot. A malicious validator might therefore aim to control as much staked ether as possible. 33% of the staked ether is a benchmark for an attacker because with anything greater than this amount they have the ability to prevent the chain from finalizing without having to finally control the actions of the other validators. They can simply all disappear together. If 1/3 or more of the staked ether is maliciously attesting or failing to attest, then a 2/3 supermajority cannot exist and the chain cannot finalize. The defense against this is the inactivity leak. The inactivity leak identifies those validators that are failing to attest or attesting contrary to the majority. The staked ether owned by these non-attesting validators is gradually bled away until eventually they collectively represent less than 1/3 of the total so that the chain can finalize again. The purpose of the inactivity leak is to get the chain finalizing again. However, the attacker also loses a portion of their staked ether. Persistent inactivity across validators representing 33% of the total staked ether is very expensive even though the validators are not slashed. Assuming that the Ethereum network is asynchronous, i.e. there are delays between messages being sent and received, an attacker controlling 34% of the total stake could cause double finality. This is because the attacker can equivocate when they are chosen to be a block producer, then double vote with all of their validators. This creates a situation where a fork of the blockchain exists, each with 34% of the staked ether voting for it. Each fork only requires 50% of the remaining validators to vote in its favor for both forks to be supported by a supermajority, in which case both chains can finalize, because 34% of attackers' validators plus half of remaining 66% equals 67% on each fork. The competing blocks would each have to be received by about 50% of the honest validators, so this attack is viable only when the attacker has some degree of control over the timing of messages propagating over the network so that they can nudge half the honest validators onto each chain. The attacker would necessarily destroy their entire stake, 34% of 10 million ether with today's validator set, to achieve this double finality because 34% of their validators would be double voting. Simultaneously, a slashable offense with the maximum correlation penalty. The defense against this attack is the very large cost of destroying 34% of the total staked ether. Recovering from this attack would require the Ethereum community to coordinate out of band and agree to follow one or other of the forks and ignore the other. Attackers using 50% of the total stake. At 50% of the staked ether, a mischievous group of validators could theoretically split the chain into two equally sized forks and then simply use their entire 50% stake to vote contrarily to the honest validator set, thereby maintaining the two forks and preventing finality. The inactivity leak on both forks would eventually lead both chains to finalize. At this point, the only option is to fall back on a social recovery. It is very unlikely that an adversarial group of validators could consistently control precisely 50% of the total stake given a degree of flux in honest validator numbers. Network latency, etc. The huge cost of mounting such an attack combined with the low likelihood of success appears to be a strong disincentive for a rational attacker. Especially when a small additional investment in obtaining more than 50% unlocks a lot more power. At 50% of the total stake, the attacker could dominate the fork choice algorithm. In this case, the attacker would be able to attest with the majority vote, giving them sufficient control to do short reorgs without needing to fool honest clients. The honest validators would follow suit because their fork choice algorithm would also see the attacker's favored chain as the heaviest, so the chain could finalize. This enables the attacker to censor certain transactions, do short-range reorgs and extract maximum MEV by reordering blocks in their favor. The defense against this is the huge cost of a majority stake, currently just under $19 billion USD, which is put at risk by an attacker because the social layer is likely to step in and adopt an honest minority fork, devaluing the attacker's stake dramatically. Attackers using equals 66% of the total stake. An attacker with 66% or more of the total staked ether can finalize their preferred chain without having to coerce any honest validators. The attacker can simply vote for their preferred fork and then finalize it, simply because they can vote with a dishonest supermajority. As the supermajority stakeholder, the attacker would always control the contents of the finalized blocks, with the power to spend, rewind, and spend again, censor certain transactions and reorg the chain at will. By purchasing additional ether to control 66% rather than 51%, the attacker is effectively buying the ability to do ex-post reorgs and finality reversions, i.e. change the past as well as control the future. The only real defenses here are the enormous cost of 66% of the total staked ether, and the option to fall back to the social layer to coordinate adoption of an alternative fork. We can explore this in more detail in the next section. People, the last line of defense. If the dishonest validators manage to finalize their preferred version of the chain, the Ethereum community is put in a difficult situation. The canonical chain includes a dishonest section baked into its history, while honest validators can end up being punished for attesting to an alternative, honest, chain. Note that a finalized but incorrect chain could also arise from a bug in a majority client. In the end, the ultimate fallback is to rely on the social layer, layer 0, to resolve the situation. One of the strengths of Ethereum's POS consensus is that there are a range of defensive strategies that the community can employ in the face of an attack. A minimal response could be to forcibly exit the attacker's validators from the network without any additional penalty. To re-enter the network, the attacker would have to join an activation queue that ensures the validator set grows gradually. For example, adding enough validators to double the amount of staked ether takes about 200 days, effectively buying the honest validators 200 days before the attacker can attempt another 51% attack. However, the community could also decide to penalize the attacker more harshly, by revoking past rewards or burning some portion, up to 100%, of their staked capital. Whatever the penalty imposed on the attacker, the community also has to decide together whether the dishonest chain despite being the one favored by the fork choice algorithm coded into the Ethereum clients, is in fact invalid and that the community should build on top of the honest chain instead. Honest validators could collectively agree to build on top of a community-accepted fork of the Ethereum blockchain that might, for example, have forked off the canonical chain before the attack started or have the attacker's validators forcibly removed. Honest validators would be incentivized to build on this chain because they would avoid the penalties applied to them for failing, rightly, to attest to the attacker's chain. Exchanges, on-ramps and applications built on Ethereum would presumably prefer to be on the honest chain and would follow the honest validators to the honest blockchain. However, this would be a substantial governance challenge. Some users and validators would undoubtedly lose out as a result of the switch back to the honest chain. Transactions in blocks validated after the attack could potentially be rolled back, disrupting the application layer, and it quite simply undermines the ethics of some users who tend to believe code is law. Exchanges and applications will most likely have linked off-chain actions to on-chain transactions that may now be rolled back, starting a cascade of retractions and revisions that would be hard to unpick fairly, especially if ill-gotten gains have been mixed, deposited into DeFi or other derivatives with secondary effects for honest users. Undoubtedly some users, perhaps even institutional ones, would have already benefited from the dishonest chain either by being shrewd or by serendipity, and might oppose a fork to protect their gains. There have been calls to rehearse the community response to 51% attacks so that a sensible coordinated mitigation could be executed quickly. There is some useful discussion by Vitalik on ethreseer.ch here and on Twitter here. The aim of a coordinated social response should be to be very targeted and specific about punishing the attacker and minimizing effects for other users. Governance is already a complicated topic. Managing a layer 0 emergency response to a dishonest finalizing chain would undoubtedly be challenging for the Ethereum community, but it has happened, twice, in Ethereum's history. Nevertheless, there is something fairly satisfying in the final fallback sitting in meat space. Ultimately, even with this phenomenal stack of technology above us, if the worst were ever to happen, real people would have to coordinate their way out of it. Summary. This page explored some of the ways attackers might attempt to exploit Ethereum's proof-of-stake consensus protocol. Reorgs and finality delays were explored for attackers with increasing proportions of the total staked ether. Overall, a richer attacker has more chance of success because their stake translates to voting power they can use to influence the contents of future blocks. At certain threshold amounts of staked ether, the attacker's power levels up. 33%, finality delay. 34%, finality delay, double finality. 51%, finality delay, double finality, censorship, control over blockchain future. 66%, finality delay, double finality, censorship, control over blockchain future and past. There are also a range of more sophisticated attacks that require small amounts of staked ether but rely upon a very sophisticated attacker having fine control over message timing to sway the honest validator set in their favor. Overall, despite these potential attack vectors, the risk of a successful attack is low, certainly lower than proof-of-work equivalents. This is because of the huge cost of the staked ether put at risk by an attacker aiming to overwhelm honest validators with their voting power. The built-in carrot and stick incentive layer protects against most malfeasance, especially for low-stake attackers. More subtle bouncing and balancing attacks are also unlikely to succeed because real network conditions make the fine control of message delivery to specific subsets of validators very difficult to achieve, and client teams have quickly closed the known bouncing, balancing, and avalanche attack vectors with simple patches. 34%, 51%, or 66% attacks would likely require out-of-band social coordination to resolve. While this would likely be painful for the community, the ability for a community to respond out-of-band is a strong disincentive for an attacker. The Ethereum social layer is the ultimate backstop. A technically successful attack could still be neutered by the community agreeing to adopt an honest fork. There would be a race between the attacker and the Ethereum community. The billions of dollars spent on a 66% attack would probably be obliterated by a successful social coordination attack if it was delivered quickly enough, leaving the attacker with heavy bags of illiquid staked ether on a known dishonest chain ignored by the Ethereum community. The likelihood that this would end up being profitable for the attacker is sufficiently low as to be an effective deterrent. This is why investment in maintaining a cohesive social layer with tightly aligned values is so important. Further reading. More keys in proof-of-stake Ethereum.
I have to be honest, after reading that first part, like I don't like this at all. I mean, I think it's very impressive the amount of work these people did and how complex everything is. Like, it's impressive, but at the same time, it feels like after I obviously don't understand everything perfectly, and I might be missing a lot of things, but it feels like that my intuition tells me that there can't be a way for this to work long term. I think like it might work for some time, but then eventually it's gonna fail at some point if it stays like this. So I think that there must be other ways to make this in a better way. So I want to study the other protocols as well to understand how they are different, because I just don't see, like, from what I understood, if there is a big enough, a rich enough attacker, then the assumption is that the community has to work together to prevent, and it's just like, it seems very like a bunch of different assumptions stack on top of each other, and it's not strong enough to be something that is going to be sustainable and resilient in different situations, and especially if it scales more and more and there's more and more money involved and more complexity. Like, I don't see how this works. But like I said before, like it is definitely impressive, the amount of stuff they did, and also I'm not really sure if I understand everything correctly. There's a lot of stuff that I might be missing and that I might have to study more to understand better, like the exact nuances of the game theory of the algorithms. But from that explanation, the way that is designed, like I don't like it at all. I think it's too much assumptions. And that's only the consensus part. There's also the assumptions that are made for the block building part and the whole MEV thing. Like I don't see. I think that Ethereum is not gonna be one of the big blockchains in the future, probably. I think what's gonna happen is someone's gonna come up, or they already did, come up with another blockchain from the start that makes everything that Ethereum does, but in a much better way. So I think it's a similar pattern that is going on here with the thing about MySpace and Facebook, for example. I think Ethereum is the MySpace of the blockchain, and then there's Facebook that is coming. That's the intuition that I have. So the question is, how would that Facebook look like? And I think it might be a different consensus algorithm. So it's probably going to be a different consensus algorithm and a different way to handle MEV. And I think the core fundamentals of blockchains are the cryptography, the consensus, and the flow of information. So those are the three pillars, I think. And MEV is going to be the relationship between the consensus and the flow of information. And through that, you have all the complexity that is born. In the cryptography, like zero knowledge proofs and things like that, there are a bunch of mathematical assumptions over the NP equal to P thing, whether or not NP is equal to P, because they're gonna be resumed through a bunch of polynomial interactions. That's the assumption is that they are a trapdoor function where it's only one way. It's easy to calculate if you have the private key, but in order to reverse the calculations is almost impossible. And they're related to prime numbers, which may or may not be true, depending. And this is the thing as well. But that's I think is the one that is the least, like the highest, that I have the highest confidence on, which like, because even if it is reversible, there are several other things that are going to break down if that's not resilient. So I don't think that like it's too big of a deal to rely on that, because it might be the case that there are other types of mathematics that allow us to solve these problems in a way that we didn't thought about before. Because mathematics is a consequence of the assumptions of the human mind over space-time. Like it's the connection between past and future that creates the logic of mathematics. That is the geometry you perceive. So there might be some form of mathematics that maps to a higher dimensional plane. That is a different geometry that has higher resolution and allows us to reduce the complexity, which I think is definitely the case based on Donald Hoffman, which I believe completely that that's the case, where there's higher dimensions, and then because this is the stuff that he talked about in the podcast that I listened yesterday, that space-time is doomed, and they were able to prove that there's these higher dimensional structures, and that if you do calculations with them, then everything becomes far more simpler, because you're not using space-time. So space-time is the wrong data structure, it's not fundamental. And I think that makes a lot of sense. So based on that, there might be new mathematics that make the whole relativistic notion of NP and P to be different than they are today. Like it still might be the case that they are asymmetrical and that you can't reverse, but they might be asymmetrical in different ways that change the boundary of the asymmetry, which would make the hash functions that we have today to be inefficient because then we discover some type of algorithm based on a higher dimensional plane that is capable of reversing the function without having to do all the calculations that we assume that we have to do nowadays to reverse the function. But I think that out of those pillars, that's the least, like the one that has the least importance, because it's probably higher probability that is going to be sustainable for a long time. I think that the other two are far more important, and I think it seems like that Ethereum has the wrong approach in my eyes, as at least so far, which is both the consensus and the network, the flow of information, and how they are correlated with each other. I think I wanna finish this section on proof of stake. It's probably not gonna probably not gonna have enough time today to study the source code because there's so much stuff to learn. I mean, it's ridiculous. The more I read the stuff, I start opening all of the tabs, and it's like it feels like an endless rabbit hole. It's pretty crazy. So I'm probably gonna read as much as I can today of all of this stuff, and then start working on studying the algorithms tomorrow. And I think enough. Today's already enough. I already looked at some portions of the project, so I think it's probably better to do it like this, where I'm reading these articles and then I'm studying the source code and going back and forth, because that way I think that if I just study the source code, it might be too hard to understand how all the functions are connected if I don't have a good high level understanding of how the concepts are working. And I didn't study enough proof of stake. I study more on the proof of work. So all of these things are new to me on the proof of stake side. And I assume that the project that I have here is the proof of stake version. It has to be because it's the one that is working now. So in order to understand the code, I have to understand that. But the main fundamental things that I want to understand is how the consensus work and how the unco blocks and the mempool work. Now, the other thing that I realized that reading that thing is about the rearg attack. That is when you, and it is something that I didn't, like I was thinking about and I thought that it didn't make sense, which is the whole thing about being able to propose a different order of blocks and how that is a slashable offense. And I think that makes a lot of sense, but the question that I have then is how is that possible that when it was proof of work, it worked like that? And this is the stuff that I'm trying to clarify and don't understand. I use ChatGPT, and it seems like ChatGPT says that that's how it worked, where each node has its own mempool or its own local history, and then they're going to update the local history at different rates. And what that means is, if that's true, is that they're going to have different orders of blocks that get included. So that's the thing that I don't understand how it works. And it's really confusing because at some point all of them have to have the same history, but if they transactions are getting into the node at different rates, then how is it possible for them to have different histories if they are updating in different times and then reach a consensus later on? I don't understand this. In my mind, it would make a lot more sense if they have to pass all of the transactions as soon as they receive them, or the blocks. But then it also doesn't make sense, because then each node would have to wait for all of the other nodes to send blocks, and it doesn't make sense. Like, so the whole synchronization thing is the hardest part for me, I think, so far to understand. And that's what I'm trying to clarify. But it's very difficult reading this stuff. So I'm gonna continue to read this and maybe look in the source code, but probably just gonna read all of this stuff today. I think I'll be right back before I continue.
Keys in Proof of Stake Ethereum. Last edit at Macin 3boy, Ethereum secures user assets using public-private key cryptography. The public key is used as the basis for an Ethereum address, that is, it is visible to the general public and used as a unique identifier. The private, or secret, key should only ever be accessible to an account owner. The private key is used to sign transactions and data so that cryptography can prove that the holder approves some action of a specific private key. Ethereum's keys are generated using elliptic curve cryptography. However, when Ethereum switched from proof of work to proof of stake, a new type of key was added to Ethereum. The original keys still work exactly the same as before. There were no changes to the elliptic curve-based keys securing accounts. However, users needed a new type of key for participating in proof of stake by staking ETH and running validators. This need arose from scalability challenges associated with many messages passing between large numbers of validators that required a cryptographic method that could easily be aggregated to reduce the amount of communication required for the network to come to consensus. This new type of key uses the Bonalin-Shaw chain, BLS, signature scheme. BLS enables a very efficient aggregation of signatures but also allows reverse engineering of aggregated individual validator keys and is ideal for managing actions between validators. The two types of validator keys. Before the switch to proof of stake, Ethereum users only had a single elliptic curve-based private key to access their funds. With the introduction of proof of stake, users that wished to be solo stakers also required a validator key and a withdrawal key. The validator key. The validator signing key consists of two elements. Validator private key. Validator public key. The purpose of the validator private key is to sign on-chain operations such as block proposals and attestations. Because of this, these keys must be held in a hot wallet. This flexibility has the advantage of moving validator signing keys very quickly from one device to another. However, if they have gotten lost or stolen, a thief may be able to act maliciously in a few ways. Being a proposer and signing two different beacon blocks for the same slot. Being an attester and signing an attestation that surrounds another one. Being an attester and signing two different attestations having the same target. Force a voluntary exit, which stops the validator from staking, and grants access to its ETH balance to the withdrawal key owner. The validator public key is included in the transaction data when a user deposits ETH to the staking deposit contract. This is known as the deposit data and it allows Ethereum to identify the validator. The withdrawal key. The withdrawal key will be required to move the validator balance after this is enabled in the upcoming Shanghai upgrade. Just like the validator keys, the withdrawal keys also consist of two components. Withdrawal private key. Withdrawal public key. Losing this key means losing access to the validator balance. However, the validator can still sign attestations and blocks since these actions require the validator's private key, but there is little to no incentive if the withdrawal keys are lost. Separating the validator keys from the Ethereum account keys enables multiple validators to be run by a single user. Deriving keys from a seed phrase. Deriving keys from a seed phrase. If every 32 ETH staked required a new set of two completely independent keys, key management would quickly become unwieldy, especially for users running multiple validators. Instead, multiple validator keys can be derived from a single common secret, and storing that single secret allows access to multiple validator keys. Mnemonics and paths are prominent features that users often encounter when they access their wallets. The mnemonic is a sequence of words that act as an initial seed for a private key. When combined with additional data, the mnemonic generates a hash known as the master key. This can be thought of as the root of a tree. Branches from this root can then be derived using a hierarchical path so that child nodes can exist as combinations of their parent node's hash and their index in the tree. Read about BIP32 and BIP19 standards for mnemonic-based key generation. These paths have the following structure, which will be familiar to you. The slashes in this path separate components of the private key as follows. 1 master key / purpose / coin type / This logic enables users to attach as many validators as possible to a single mnemonic phrase because the tree root can be common, and differentiation can happen at the branches. The user can derive any number of keys from the mnemonic phrase. 1m/02/3/4m, m/1. Each branch is separated by a slash, so m/2 means start with the master key and follow branch 2. In the schematic below, a single mnemonic phrase is used to store 3 withdrawal keys, each with 2 associated validators. Further reading. Proof of stake vs proof of work. When Ethereum launched, proof of stake still needed a lot of research and development before it could be trusted to secure Ethereum. Proof of work was a simpler mechanism that had already been proven by Bitcoin, meaning core developers could implement it right away to Ethereum launched. It took a further 8 years to develop proof of stake to the point where it could be implemented. This page explains the rationale behind Ethereum's switch to proof of stake from proof of work and the trade-offs involved. Security. Ethereum researchers consider proof of stake more secure than proof of work. However, it has only recently been implemented for the real Ethereum mainnet and is less time proven than proof of work. The following sections discuss the pros and cons of proof of stake's security model compared to proof of work. Cost to attack. In proof of stake, validators are required to escrow, stake, at least 32 ETH in a smart contract. Ethereum can destroy staked Ether to punish validators that misbehave. To come to consensus, at least 66% of the total staked Ether has to vote in favor of a particular set of blocks. Blocks voted for by equals 66% of the stake become finalized, meaning they can't be removed or reorganized. Attacking the network can mean preventing the chain from finalizing or ensuring a certain organization of blocks in the canonical chain that somehow benefits an attacker. This requires the attacker to divert the path of honest consensus either by accumulating a large amount of Ether and voting with it directly or tricking honest validators into voting in a particular way. Sophisticated, low-probability attacks that trick honest validators aside, the cost to attack Ethereum is the cost of the stake that an attacker has to accumulate to influence consensus in their favor. The lowest cost of attack is 33% of the total stake. An attacker holding 33% of the total stake can cause a finality delay simply by going offline. This is a relatively minor problem for the network, as there is a mechanism known as the inactivity leak that leaks stake away from offline validators until the online majority represents 66% of the stake and can finalize the chain again. It is also theoretically possible for an attacker to cause double finality with a little over 33% of the total stake by creating 2 blocks instead of 1 when they are asked to be a block producer, and then double vote with all of their validators. Each fork only requires 50% of the remaining honest validators to see each block first, so if they manage to time their messages just right, they may be able to finalize both forks. This has a low likelihood of success, but if an attacker was able to cause double finality, the Ethereum community would have to decide to follow one fork, in which case the attacker's validators would necessarily be slashed on the other. With 33% of the total stake, an attacker has a chance to have a minor finality delay, or more severe, double finality, effect on the Ethereum network. With more than 14 million ETH staked on the network in a representative price of $1,000/ETH, the minimum cost to mount these attacks is 1,000 x 14 million x 0.33. The attacker would lose this money through slashing and get ejected from the network. To attack again, they would have to accumulate 33% of the stake, again, and burn it, again. Each attempt to attack the network would cost $4.6 billion, at $1,000/ETH and 14 ETH staked. The attacker is also ejected from the network when they are slashed, and they have to join an activation queue to rejoin. This means the rate of a repeat attack is limited not only to the rate the attacker can accumulate 33% of the total stake, but also the time it takes to onboard all their validators onto the network. Each time the attacker attacks, they get much poorer, and the rest of the community gets richer, thanks to the resulting supply shock. Other attacks, such as 51% attacks or finality reversion with 66% of the total stake, require substantially more ETH and are much more costly to the attacker. Compare this to proof of work. The cost of launching an attack on proof of work Ethereum was the cost of consistently owning 50% of the total network hash rate. This amounted to the hardware and running costs of sufficient computing power to outcompete other miners to compute proof of work solutions consistently. Ethereum was mostly mined using GPUs rather than ASICs, which kept the cost down, although had Ethereum stayed on proof of work, ASIC mining may have become more popular. An adversary would have to purchase a lot of hardware and pay for the electricity to run it to attack a proof of work Ethereum network, but the total cost would be less than the cost required to accumulate enough ETH to launch an attack. A 51% attack is 20x less expensive on proof of work than proof of stake. If the attack was detected and the chain hard forked to remove their changes, the attacker could repeatedly use the same hardware to attack the new fork. Complexity. Proof of stake is much more complex than proof of work. This could be a point in favor of proof of work, as it is harder to introduce bugs or unintended effects into simpler protocols accidentally. However, the complexity has been tamed by years of research and development, simulations, and testnet implementations. The proof of stake protocol has been independently implemented by 5 separate teams, on each of the execution and consensus layers, in 5 programming languages, providing resilience against client bugs. To safely develop and test the proof of stake consensus logic, the Beacon chain was launched 2 years before proof of stake was implemented on Ethereum mainnet. The Beacon chain acted as a sandbox for proof of stake testing, as it was a live blockchain implementing the proof of stake consensus logic but without touching real Ethereum transactions, effectively just coming to consensus on itself. Once this had been stable and bug-free for a sufficient time, the Beacon chain was merged with Ethereum mainnet. This all contributed to taming the complexity of proof of stake to the point that the risk of unintended consequences or client bugs was very low. Attack surface. Proof of stake is more complex than proof of work, which means there are more potential attack vectors to handle. Instead of one peer-to-peer network connecting clients, there are 2, each implementing a separate protocol. Having one specific validator pre-selected to propose a block in each slot creates the potential for denial of service where large amounts of network traffic knock that specific validator offline. There are also ways that attackers can carefully time the release of their blocks or attestations so that they are received by a certain proportion of the honest network, influencing them to vote in certain ways. Finally, an attacker can simply accumulate sufficient ETH to stake and dominate the consensus mechanism. Each of these attack vectors has associated defenses, but they do not exist to be defended under proof of work. Decentralization. Proof of stake is more decentralized than proof of work because mining hardware arms races tend to price out individuals and small organizations. While anyone can technically start mining with modest hardware, their likelihood of receiving any reward is vanishingly small compared to institutional mining operations. With proof of stake, the cost of staking and the percentage return on that stake are the same for everyone. It currently costs 32 ETH to run a validator. On the other hand, the invention of liquid staking derivatives has led to centralization concerns because a few large providers manage large amounts of staked ETH. This is problematic and needs to be corrected as soon as possible, but it is also more nuanced than it seems. Centralized staking providers do not necessarily have centralized control of validators. Often it is just a way to create a central pool of ETH that many independent node operators can stake without every participant requiring 32 ETH of their own. The best option for Ethereum is for validators to be run locally on home computers, maximizing decentralization. This is why Ethereum resists changes that increase the hardware requirements for running a node/validator. Sustainability. Proof of stake is a carbon-cheap way to secure the blockchain. Under proof of work, miners compete for the right to mine a block. Miners are more successful when they can perform calculations faster, incentivizing investment in hardware and energy consumption. This was observed for Ethereum before it switched to proof of stake. Shortly before the transition to proof of stake, Ethereum was consuming approximately 78 TWh/year, as much as a small country. However, switching to proof of stake reduced this energy expenditure by 99.98%. Proof of stake made Ethereum an energy efficient, low issuance. Proof of stake Ethereum can pay for its security by issuing far fewer coins than proof of work Ethereum because validators do not have to pay high electricity costs. As a result, ETH can reduce its inflation or even become deflationary when large amounts of ETH are burned. Lower inflation levels mean Ethereum's security is cheaper than it was under proof of work.
It's It's almost black and white. The proof of stake is clearly superior than proof of work.
So there's a bunch of points there to
Block's
respond
proposal.
to, so I'll try to
Last
go
edited Coleman
linearly, I
Times,
guess.
January 18th, 2023. Blocks are the fundamental units of the blockchain. Blocks are discrete units of information that get passed between nodes, agreed upon and added to each node's database. This page explains how they are produced. Prerequisites. Block proposal is part of the proof of stake protocol. To help understand this page, we recommend you read about proof of stake and block architecture. Who produces blocks? Validator accounts propose blocks. Validator accounts are managed by node operators who run validator software as part of their execution and consensus clients and have deposited at least 32 ETH into the deposit contract. However, each validator is only occasionally responsible for proposing a block. Ethereum measures time in slots and epochs. Each slot is 12 seconds, and 32 slots, 6.4 minutes, make up an epoch. Every slot is an opportunity to add a new block on Ethereum. Random selection. A single validator is pseudo-randomly chosen to propose a block in each slot. There is no such thing as true randomness in a blockchain because if each node generated genuinely random numbers, they couldn't come to consensus. Instead, the aim is to make the validator selection process unpredictable. The randomness is achieved on Ethereum using an algorithm called Randao that mixes a hash from the block proposer with a seed that gets updated every block. This value is used to select a specific validator from the total validator set. The validator selection is fixed 4 epochs in advance as a way to protect against certain kinds of seed manipulation. Although validators add to Randao in each slot, the global Randao value is only updated once per epoch. To compute the index of the next block proposer, the Randao value is mixed with the slot number to give a unique value in each slot. The probability of an individual validator being selected is not simply 1/n, where n equals total active validators. Instead, it is weighted by the effective ETH balance of each validator. The maximum effective balance is 32 ETH. This means that balance 32 ETH does not lead to higher weighting than balance equals 32 ETH. Only one block proposer is selected in each slot. Under normal conditions, a single block producer creates and releases a single block in their dedicated slot. Creating 2 blocks for the same slot is a slashable offense, often known as equivocation. How is the block created? The block proposer is expected to broadcast a signed beacon block that builds on top of the most recent head of the chain according to the view of their own locally run fork choice algorithm. The fork choice algorithm applies any Q to attestations left over from the previous slot, then finds the block with the greatest accumulated weight of attestations in its history. That block is the parent of the new block created by the proposer. The block proposer creates a block by collecting data from its own local database and view of the chain. The contents of the block are shown in the snippet below. Max voluntary exits 10 sync aggregate 11 execution payload 12 show all. The Randao reveal field takes a verifiable random value that the block proposer creates by adding some of its own entropy to the accumulated Randao value from previous blocks. ETH1 data is a vote for the block proposer's view of the deposit contract, including the root of the deposit Merkle tree and the total number of deposits that enable new deposits to be verified. Graffiti is an optional field that can be used to add a message to the block. Proposer slashings and attester slashings are fields that contain proof that certain validators have committed slashable offenses according to the proposer's view of the chain. Deposits is a list of new validator deposits that the block proposer is aware of, and voluntary exits is a list of validators that wish to exit that the block proposer has heard about on the consensus layer gossip network. The sync aggregate is a vector showing which validators were previously assigned to a sync committee, a subset of validators that serve like client data, and participated in signing data. The execution payload enables information about transactions to be passed between the execution and consensus clients. The execution payload is a block of execution data that gets nested inside a beacon block. The fields inside the execution payload reflect the block structure outlined in the Ethereum yellow paper, except that there are no omers and pre-Randao exists in place of difficulty. The execution client has access to a local pool of transactions that it has heard about on its own gossip network. These transactions are executed locally to generate an updated state tree known as a post state. The transactions are included in the execution payload as a list called transactions and the post state is provided in the state root field. All of these data are collected in a beacon block, signed, and broadcast to the block proposer's peers, who propagate it onto their peers, etc. Read more about the anatomy of blocks. What happens to the block? The block is added to the block proposer's local database and broadcast to peers over the consensus layer gossip network. When a validator receives the block, it verifies the data inside it, including checking that the block has the correct parent, corresponds to the correct slot, that the proposer index is the expected one, that the Randao reveal is valid and that the proposer is not slashed. The execution payload is unbundled, and the validator's execution client re-executes the transactions in the list to check the proposed state change. Assuming the block passes all these checks, each validator adds the block to its own canonical chain. The process then starts again in the next slot. Block rewards. The block proposer receives payment for their work. There is a base reward calculated as a function of the number of active validators and their effective balances. The block proposer then receives a fraction of base reward for every valid attestation included in the block. The more validators attest to the block, the greater the block proposer's reward. There is also a reward for reporting validators that should be slashed, equal to 1/512 * effective balance for each slashed validator. More on rewards and penalties. Frequently asked questions. Last edit at Petnerup, January 12, 2023. Proof of stake is a class of algorithm that can provide security to blockchains by ensuring that assets of value are lost by attackers who act dishonestly. Proof of stake systems require a set of validators to make some asset available that can be destroyed if the validator engages in some provably dishonest behavior. Ethereum uses a proof of stake mechanism to secure the blockchain. How does proof of stake compare to proof of work? Both proof of work and proof of stake are mechanisms that economically disincentivize malicious actors from spamming or defrauding the network. In both cases, nodes that actively participate in consensus put some asset into the network that they will lose if they misbehave. In proof of work, this asset is energy. The node, known as a miner, runs an algorithm that aims to compute a value faster than any other node. The fastest node has the right to propose a block to the chain. To change the history of the chain or dominate the block proposal, a miner would have to have so much computing power that they always win the race. This is prohibitively expensive and difficult to execute, protecting the chain from attacks. The energy required to mine using proof of work is a real-world asset that miners pay for. Proof of stake requires nodes, known as validators, to explicitly submit a crypto asset to a smart contract. If a validator misbehaves, this crypto can be destroyed because they are staking their assets directly into the chain instead of indirectly via energy expenditure. Proof of work is much more energy hungry because electricity is burned in the mining process. Proof of stake, on the other hand, requires only a very small amount of energy. Ethereum validators can even run on a low-powered device such as Raspberry Pi. Ethereum's proof of stake mechanism is thought to be more secure than proof of work because the cost to attack is greater, and the consequences to an attacker are more severe. Proof of work versus proof of stake is a contentious topic. Vitalik Buterin's blog and the debate between Justin Drake and Lynn Alden give a good summary of the arguments. Is proof of stake energy efficient? Yes. Nodes on a proof of stake network use a tiny amount of energy. A third-party study concluded that the entire proof of stake Ethereum network consumes around 0.0026 TW. Module Bulletproof's Notes Inner Product Proof. This module contains notes on how and why the inner product proof protocol works. Inner product proof. First, let's observe that the prover can simply send vectors L, X, and R, X, and the verifier can check directly that the inner product T, X, and commitment PP provided in the protocols 1 and 2 are correct. This will not leak information, the secret bits in these vectors are blinded, but will require us to transfer 2 end-to-end scalars between a prover and a verifier. To minimize the bandwidth cost, we will use the inner product argument protocol, which enables us to prove indirectly and with O, log, N, communication cost. That a given inner product T, X, and a commitment PP are related as T, X, equals L, X, R, X, P equals L, X, G plus R, X, HT, X, P equals L, X, R, X, equals L, X, G plus R, X, H to make the presentation cleaner. We will change the notation to one used specifically in the inner product argument, which is not to be confused with the notation in the range proof protocol. A B set membership symbols EPNGH set membership symbol GNC, HCP set membership symbols EPN set membership symbol GN equals AB equals AG plus BH within B. Let's combine these two statements into one equation using an indeterminate variable W set membership symbols EP times W set membership symbols EP times and multiplying the second BWBPCWB equals AG plus BH ABWB. Let's simplify the resulting equation. H plus ABQ. The combined equation is useful because it will allow us to compress each vector in half and arrive to the same form. By doing such compression LGN times, we will end up with an equation where both vectors are one element long and we can simply transmit them to check the final equality directly. If the prover can demonstrate that the above PP has such structure over generators GG, HH, and QQ for all W set membership symbols EPW set membership symbols EP, then the original PP and CC must satisfy the original relation, P equals AG plus BHC equals AB. Let's introduce an indeterminate variable UK set membership symbols EP times UK set membership symbols EP times and compress. The powers of UK are chosen so they cancel out in the inner products of interest as will be shown below. Let pk equals P and define pk1 using the same equation as for pk H, k1, plus a, k1, b, k1, q, expanding it in terms of the BLO UK1 plus UKBQ, BLO, q. We now see that the left two columns in the above equation is the definition of pk, while various cross terms on the right are separated from pk by an indeterminate variable UK. Let's group all terms with UK2 as BLO QPK1 LKRK equals PK. Then if the statement about compressed vectors is proven to be true, it will follow that the original statement about uncompressed vectors is also true with an overwhelming probability. We can compress the resulting statement about pk1 using one more indeterminate variable UK1 in the same way as we used UK in a Simple summary. Introduce a new Verkle state tree alongside the existing hexarray Patricia tree. After the hard fork, the Verkle tree stores all edits to state in a copy of all accessed state, and the hexarray Patricia tree can no longer be modified. This is a first step in a multi-phase transition to Ethereum exclusively relying on Verkle trees to store execution state. Motivation. Verkle trees solve the key problem standing in the way of Ethereum being stateless client-friendly, witness sizes. A witness accessing an account in today's hexarray Patricia tree is, in the average case, close to 3 KB, and in the worst case it may be 3 times larger. Assuming a worst case of 6,000 accesses per block, 15 M gas/2,500 gas per access, this corresponds to a witness size of 18 MB, which is too large to safely broadcast through a P2P network within a 12-second slot. Verkle trees reduce witness sizes to 200 bytes per account in the average case, allowing stateless client witnesses to be acceptably small. Specification. Verkle tree definition. We define a Verkle tree here by providing the function to compute the root commitment given a set of 32-byte keys and 32-byte values. Algorithms for updating and inserting values are up to the implementer. The only requirement is that the root commitment after the update must continue to match the value computed from this specification. We will then define an embedding that provides the 32-byte key at which any particular piece of state information, account headers, code, storage, should be stored. Hashtag Bandersnatch curve order Bandersnatch modulus equals /1310896893793715589344649145930957864091558934404070864033067296876728001 Hashtag Bandersnatch Peterson basis of length 256 Peterson basis equals Verkle node width equals len, Peterson basis, def crypto field, point, dash int, hashtag not collision resistant. Not random oracle. Hashtag binding for Peterson commitments. Assert isinstance, point, if point equals bandersnatch.z, return 0 else, return int.firm bytes, point.serialize, little, %bandersnatch modulus def compute commitment root, children. Sequence int, dash point, o equals bandersnatch.z for generator, child in zip, Peterson basis, children o equals bandersnatch.add, o, bandersnatch.mul, generator. Child, return o def extension and suffix tree, stem, bytes 31, values, dict byte, bytes 32, dash int, subleaves equals 0 asterisk 512 for suffix, value in values.items. Subleaves 2 asterisk suffix equals int.firm bytes, value 16, little, plus 2 128 subleaves 2 asterisk suffix plus 1 equals int.firm bytes, value 16, little, C1 equals compute commitment root, subleaves. 256, C2 equals compute commitment root, subleaves 256, return compute commitment root, 1, hashtag extension marker int.firm bytes, stem, note that a value of 0 is not the same thing as a position being empty, a position being empty is represented as 0 in the bottom layer commitment. But a position being 0 is represented by a different value in the suffix tree commitment, 2128 is added to value lower to distinguish it from empty. This distinction between 0 and empty is not a property of the existing Patricia tree, but it is a property of the proposed Verkle tree. In the rest of this document, saving or reading a number at some position in the Verkle tree will mean saving or reading the 32-byte little endian encoding of that number. Illustration. This is an illustration of the tree structure. Tree embedding. Instead of a two-layer structure as in the Patricia tree, in the Verkle tree we will embed all information into a single key, value tree. This section specifies which tree keys store the information, account header data, code, storage, in the state. Parameter value, it's a required invariant that Verkle node width code offset header storage offset and that header storage offset is greater than the leaf keys. Additionally, main storage offset must be a power of Verkle node width. Note that addresses are always passed around as an address 32. To convert existing addresses to address 32, prepend with 12 0 bytes, header values. These are the positions in the tree at which block header fields of an account are stored. Def Peterson hash, in, bytes, dash bytes 32, assert len, in. 16 asterisk, I plus 1, for I in range, 255, return compute commitment root, ints, dot serialize, def get tree key, address 32, tree index, int, subindex, int. When any account header field is set, the version is also set to 0. The code and code size fields are set upon contract creation. Code. Def get tree key for code at chunk I stores a 32-byte value, where bytes 1.31 are bytes I31, I plus 1, 31, 1 of the code, i.e. the ith 31-byte slice of it, and byte 0 is the number of leading bytes that are part of push data, e.g. If part of the code is push 4 99 98 97 96 push 1 128 mistore, where is the position where a new chunk begins, then the encoding of the latter chunk would begin 2 97 96 push 1 128. For precision, here is an implementation of code chunkification. Push offset equals 95 push 1 equals push offset plus 1 push 32 equals push offset plus 32 def chunkify code, bytes, dash sequence bytes 32, hashtag pad to multiple of 31 bytes if len, code, %31. Equals 0, code plus equals b, backslash x00, asterisk, 31, len, code, %31, hashtag figure out how much push data there is after plus including each byte bytes to exec data equals 0 asterisk, len, code, plus 32, pos equals 0 while pos. If push 1. Bytes to exec data pos plus x equals push data bytes, x, storage. Def get tree key for storage slot, address 32, storage key, int if storage key. POS equals main storage offset plus store. Note that storage slots in the same size Verkle node width range, i.e. arrange the form x asterisk Verkle node width. X plus 1, asterisk Verkle node width 1, are all, with the exception of the header storage offset special case, part of a single commitment. This is an optimization to make witnesses more efficient when related storage slots are accessed together. If desired, this optimization can be exposed to the gas schedule, making it more gas efficient to make contracts that store related slots together. However, Solidity already stores in this way by default. Fork. At block number fork height, we replace the state, Patricia tree structure with the states, tuple Patricia tree, Verkle tree structure. The Patricia tree carries over the data from the previous Patricia tree. The Verkle tree starts off empty, though note that it may become non-empty even during block number fork height as a result of activity within that block itself. From that point on, the Patricia tree is immutable, and all modifications happen to the Verkle tree. Data is saved to the Verkle tree when those fields are modified, or when they are simply accessed. State is read by first attempting to read the Verkle tree, and only if the Verkle tree is empty at a particular position attempting to read the Patricia tree. Note that setting a value to 0, whether balance or a storage key or anything else, sets the value in the tree at the appropriate position to 0, not empty. Access events. We define access events as follows. When an access event takes place, the accessed data is saved to the Verkle tree, even if it was not modified. An access event is of the form, address, subkey, leafkey, determining what data is being accessed. Access events for account headers. When a non-precompile address is the target of a call code, delegate call, self-destruct, xcodesize, or xcode a copy of code, or is the target address of a contract creation whose init code starts execution, process these access events. Address, 0, version leafkey, address, 0, codesize leafkey. If a call is value-bearing, i.e. it transfers non-zero way, whether or not the callee is a precompile, process these two access events. Caller address, 0, balance after. When a contract creation is initialized, process these access events. Contract address, 0, version leafkey. When a contract is created, process these access events. Contract address, 0, version leaf. If the balance subcode is called targeting some address, process this access event. If the self-destruct subcode is called by some caller address targeting some target address, regardless of whether it's value-bearing or not, process access events of the form. If the xcode hash subcode is called targeting some address, process an access event of the form. Access events for storage. Slowed and store up codes with a given address and key process an access event of the form. Address, tree key, subkey, where tree key and subkey are computed as follows. Def get storage slot tree keys, storage key, int, dash int, if storage key. Access events for code. In the conditions below, chunked is accessed is understood to mean an access event of the form. Address, chunked plus 128, / 256, chunked plus 128, % 256. At each step of EVM execution, if and only if. PC. Chunk. PC / chunk size. Where. PC. Is the current program counter of the callee is accessed. In particular, note the following corner cases. The destination of a jump, or positively evaluated jumpy, is considered to be accessed, even if the destination is not a jump dest or is inside push data. The destination of a jumpy is not considered to be accessed if the jump conditional is false. The destination of a jump is not considered to be accessed if the execution gets to the jump up code but does not have enough gas to pay for the gas cost of executing the jump up code, including chunk. Access cost if the jump is the first up code in a not yet accessed chunk. The destination of a jump is not considered to be accessed if it is beyond the code. Destination equals len, code. If code stops execution by walking past the end of the code, PC equals len, code, is not considered to be accessed. If the current step of EVM execution is a push n, all chunks, PC / chunk size. If a non-zero read size. Code copy. Or. Xcode copy. Read bytes. X, Y, of the accessed contract are accessed. Transactions. For a transaction, make these access events. tx.origin, 0, version leafkey, tx.origin, 0, balance, witness gas costs. Constant value witness bring, when executing a transaction, maintain two sets. Accessed sub, when an access event of, address, subkey, leafkey, occurs, perform the following checks. If, address, subkey, is not in accessed subtrees, charge witness bring cost gas and add that tuple to accessed subtrees, miscellaneous. The self-destruct code is renamed to sendle, and now only immediately moves all eth in the account to the target. It no longer destroys code or storage or alters the nonce. All refunds are removed. Rationale. This implements all of the logic in transitioning to a Verkle tree, and at the same time reforms gas costs, but does so in a minimally disruptive way that does not require simultaneously changing the whole tree structure. Instead, we add a new Verkle tree that starts out empty, and only new changes to state and copies of accessed state are stored in the tree. The Patricia tree continues to exist, but is frozen. This sets the stage for a future hard fork that swaps the Patricia tree in place with a Verkle tree storing the same data. Unlike EIP 2584, this replacement Verkle tree does not need to be computed by clients in real time. Instead, because the Patricia tree would at that point be fixed, the replacement Verkle tree can be computed off-chain. Verkle tree design. The Verkle tree uses a single-layer tree structure with 32-byte keys and values for several reasons. Simplicity, working with the abstraction of a key/value store makes it easier to write code dealing with the tree, e.g. database reading/writing, caching, syncing, proof creation and verification, as well as to upgrade it to other trees in the future. Additionally, witness gas rules can become simpler and clearer. Uniformity, the state is uniformly spread out throughout the tree. Even if a single contract has many millions of storage slots, the contract's storage slots are not concentrated in one place. This is useful for state syncing algorithms. Additionally, it helps reduce the effectiveness of unbalanced tree filling attacks. Extensibility, account headers and code being in the same structure as storage makes it easier to extend the features of both, and even add new structures if later desired. The single-layer tree design does have a major weakness, the inability to deal with entire storage trees as a single object. This is why this EIP includes removing most of the functionality of self-destruct. If absolutely desired, self-destruct's functionality could be kept by adding and incrementing an account stat offset parameter that increments every time an account self-destructs, but this would increase complexity. Gas reform. Gas costs for reading storage and code are reformed to more closely reflect the gas costs under the new Verkle tree design. Witness chunk cost is set to charge 6.25 gas per byte for chunks, and witness branch cost is set to charge 13.2 gas per byte for branches on average, assuming 144 byte branch length, and 2.5 gas per byte in the worst case if an attacker fills the tree with keys deliberately computed to maximize proof length. The main differences from gas costs in Berlin are 200 gas charged per 31 byte chunk of code. This has been estimated to increase average gas usage by 6-12%. See this analysis suggesting 10 to 20% gas usage increases at a 350 gas per chunk level. Cost for accessing adjacent storage slots, key 1/256 E. Cost for accessing storage slots 0.63 decreases from 2100 to 200, including the first storage slot. This is likely to significantly improve performance of many existing contracts, which use those storage slots for single persistent variables. Gains from the latter two properties have not yet been analyzed, but are likely to significantly offset the losses from the first property. It's likely that once compilers adapt to these rules, efficiency will increase further. The precise specification of when access events take place, which makes up most of the complexity of the gas repricing, is necessary to clearly specify when data needs to be saved to the period 1 tree. Forward compatibility. After the fork, there are two trees, A, no longer changing, Hexari Patricia tree for period 0 and a Verkle tree for period 1. At that point we have forward compatibility with two paths. Fully implement state expiry, with a subsequent EIP that swaps out the Patricia tree root for a Verkle tree root, begins period 2 and schedules future periods, see the roadmap. Abandon state expiry, and slowly move all period 0 data into period 1, so we just have weak statelessness. Hence, while this EIP offers a very convenient path to implementing state expiry, it does not force that course of action, and it does leave open the door to simply sticking with weak statelessness. Backward compatibility. The three main backwards compatibility breaking changes are self-destruct neutering, see here for a document stating the case for doing this despite the backwards compatibility loss. Gas costs for code chunk access making some applications less economically viable. Tree structure change makes in EVM proofs of historical state no longer work. 2. Can be mitigated by increasing the gas limit at the same time as implementing this EIP, reducing the risk that applications will no longer work at all due to transaction gas usage rising above the block gas limit. 3. Cannot be mitigated this time, but this proposal could be implemented to make this no longer a concern for any tree structure changes in the future. Possible future extension, gas costs for writes. https://notes.ethereum
I'm already getting tired, so I'm going to stop here and I'm going to watch these videos while I play poker off stream. And then tomorrow I'm gonna read the articles here. And read the yellow paper again. And also I need to read these 2 chapters again. And after I do all that, or in the middle of that, then I might start streaming and study this, continue to study the source code, and then hopefully start looking at the functions and the files inside. I'm probably gonna do something similar than what I did today, but for the other folders. So what I did today was just to see on the peer-to-peer what each folder is about, and then I'm gonna do that for the core parts as well. And I'm trying to understand what are the ones that are related to the mempool. It's obviously not gonna be perfect because GPT is not with the correct version. It doesn't have the correct version on the model, so but at least I can get a start. And I think from this one it seems like the transport is gonna be really important because it is responsible for the mempool, I think, for a lot of parts of the mempool. So I'm gonna try to understand what are the folders that's like I'm going to try to simplify as much as possible so I can study the functions that are related to this problem. And also I have to think more about to define better what I'm trying to understand about the relationship between the mempool and how the mempool propagates across the network. I think the updating mechanism of each node, that's what I want to understand, how they keep the synchronization of the history in both proof of work and now proof of stake. So I'm going to try to find out what are the folders that are responsible for that and what are the files that are responsible for that. Once I have a good idea of that, then I look into each file specifically and try to understand the functions. So I'm probably gonna look back tomorrow. If not, then almost definitely 2 days from now.